Yes, ma'am.
You take care of the moderation today. बीच में मुझे जाना पड़ेगा.
Okay, ma'am.
And the other thing is just post in the Telegraph that we are starting at 11 o'clock, and today's morning session will go up till 1:30, and second session will start at 2:30. Because Dr. Aninya Datta said he needs a laptop which will be free only after 2 o'clock.
Okay, ma'am.
And we'll put up the feedback form at 4:15.
4:50.
4:15.
4:15.
And withdraw it by 4:45 max.
Okay, ma'am.
Not more than that, because people will unnecessarily, even if they don't sit, then they'll log in.
Mm-hmm. Yes,
And
ma'am.
we'll not post the
ma'am,
feedback in the Telegraph.
हाँ मैम एक्चुअली अशोक सर का मैसेज था मॉर्निंग में. ही वाज आस्किंग फॉर द शेड्यूल.
A schedule, you can tell him 2:30 the second session starts. It will finish at 4:30, yeah. So okay. Let him be ready by 4:25 or so. 4:15 say let him be online, unless he's attending the whole session.
Okay, ma'am.
I've asked Dr. Arindam to join by 10:45. Has anybody lined up Khalida in the YouTube? Khalida?
Yes, madam. Yes, madam.
Yes, ma'am. 11 students.
ठीक आएंगे. Yes, Deepa, good morning. Hello? Oh gosh, I should be.
Good morning, all.
Good morning, sir.
Hello?
Yes, sir. We can hear you. Good morning.
लक्ष्मी, उनको सर्टिफिकेट के बारे में भी बोलना पड़ेगा ना. हेलो हेलो.
All of you, please see my WhatsApp message in the group.
Hello.
Good morning, Dr. Arindam.
Good morning. So I think this is okay,
Yeah.
right? You can hear me.
Yeah, just slide sharing. Can you just check?
I checked it. It's fine.
Okay.
I'm doing it with two computers now, so that in one I can do this, and the other one I can. So I'm logged into two accounts basically on 2 points. I'm just going to take out something before I
Yeah.
Start. Okay.
Yeah.
But my voice is clear, correct?
Yes, yes, it is.
Mhm. So my battery is going to last for about 2.5 hours. So I guess that's how I mean, at least the presentation part. Do we have enough participants?
Khalida, could you see how many are there?
Ma'am, 57.
Yeah, that's good enough to start.
Shall we wait for a few minutes?
Okay, maybe 2-3 minutes more.
I can, or else I can do a kind of a recap. But let me first try to share it again. Where is that button? Okay. Okay, can everybody see it?
Yes.
Yes, sir.
I'll make it full screen.
Yes,
Yeah.
sir, we are able to see.
Okay, in YouTube it is not coming up, but
Yeah, will come, sir. There is a
Time lag.
okay.
time lag.
The chat box I wanted to see. Um, yes, the chat box is here so that I can take the question. So I'll do the same thing as yesterday. Is that okay?
Yeah, fine. After every
I'll,
half an hour question and answer.
after, yeah. So I'll probably
So
have.
Khalida will moderate, sir.
It's okay. I
And
think I'll ask her when I need because
okay,
on
fine,
the
fine.
questions that comes from the Microsoft Teams, she can.
Okay,
But
okay.
the ones that are there in the
YouTube.
YouTube, I can actually see it. So
Okay, fine.
uh, I can see it pretty clearly.
So would you like to start now?
Yes, perhaps we should just start then.
Yeah. Khalida?
Yes, ma'am.
Actually,
Yeah.
yeah, that's fine. Let me get some water.
A very good morning to all. On behalf of VG Vase College of Arts, Science and Commerce, Department of Chemistry, I, Khalida Sheikh, welcome you all to the second day of the webinar on quantum chemistry and symmetry in chemistry, organized in association with the Royal Society of Chemistry, West India section. We are already familiar with our first speaker for the day. So without any further delay, I now invite Professor Arindam Chaudhary to proceed with his session on quantum chemistry. Over to you, sir.
Okay, thank you, Khalida. Very good morning to all of you, and
Welcome.
welcome back. Am I audible? Okay.
Yes, sir. Perfect.
All right. I'll just ask these guys. I'm not sure whether uh, there's people in the. Yeah. Okay. They should be able to see me. All right. Um, so what I'll do is I see that the number of participants are less right now. So what I will do is I will do a little bit of recap and then move on. All right. In the meantime, maybe in 5 minutes, I'll try to do a quick recap and then move on. That will help people who are already here to remember what we did yesterday, and uh, people who are coming late can join when we start the new topics today. All right. So essentially, what we found out was that in the early 1900s, physicists, scientists realized that particles is not a particle, wave is not a wave. Particles and waves both are very weird. We don't know what they are, and they can act like both particles and waves at the same time. And this is especially true for quantum mechanical particles or those submicroscopic particles like electrons and atoms and protons, etc. Now, so please remember, this is important. That's why I flashed it again here. That whenever I say particle, okay, we are going to talk about particle in a box today. We actually don't really mean it's a true particle. It's actually a wavicle or a wave particle. All right, this is something that I want everyone to remember here. All right. And then with the uncertainty principle concept that Heisenberg introduced, that nothing is deterministic, there was a huge problem, and essentially we realized that we cannot describe these microscopic, submicroscopic systems, atomic systems, or quantum mechanical systems by our own physics. We have to develop new physics to understand, or new theories to understand what their dynamics is. And we cannot do it in a random way. We have to do it in a probabilistic fashion. And that is what is called the quantum mechanical way. It cannot be deterministic like Newton's laws. It has to be indeterministic. So we have to take a mathematical probabilistic description, and we have to incorporate some wave-like property or wave-like equation for matter like electrons, what is known matter as like electrons, and protons and atoms and molecules. And in 1925 or so, Schrodinger came up with this very interesting equation. That's what I told you. That's called the Schrodinger equation or the time-dependent Schrodinger equation. How we got it, we don't know. It came out of Schrodinger's mind. And that therefore it forms a postulate of quantum mechanics. And just because we are doing a new theory, which basically now requires some set of rules that we need to follow, those founding fathers came up with 4 or 5 sets of rules, and we talked about these rules or these postulates, which we cannot question. We cannot question the postulates. We have to assume they to be true. We consider them as axioms, and we see that okay, if we consider these as axioms or we believe in these things, these rules or postulates, what do we get? And then we talked a little bit about wave function, meaning of the wave function. We said we don't know what the meaning of the wave function is, but what Born said was the square of the wave function or the complex conjugate times the wave function is basically the probability density. And so you can calculate of finding a particle at a point. So that automatically led us to the idea of normalization, which basically means that this integral that is shown here at the bottom, that integral over all space has to be 1 because the probability of finding the particle over all space has to be equal to 1. And then we said, okay, this 2 postulates. One is this Born's idea of what is a wave function or the square of the wave function is, and Born's interpretation and the Schrodinger equation. They both lead there. It's a second order differential equation, partial differential equation. So they automatically lead to some restrictions on the wave functions. And we discussed about that a little bit. We talked about these special cases, which are called this single point, discontinuities. We said we don't worry about this right now. It's a very special case. Only people who are working in the field actually need to know that. Then we gave some examples, and then we talked about operators. What it means, we said they perturb the system. They're like the act of doing a measurement. And we said that one of the postulates essentially says that for every observable that you can measure, and the word measure itself relates to this idea of operators, there is a quantum mechanical operator. Okay, and we did not know how they came up with this momentum operator, but if we assume that's why it's a postulate. If we assume this is the momentum operator of this form of iota h cross del del x in one dimension, then we can derive all the rest of the operators and everything becomes consistent. Now, the other thing that we discussed was that the Schrodinger equation. Okay, before I go into the Schrodinger equation, we discussed about eigenvalues, what is an eigenvalue and what is an eigenfunction. And we said that one of the postulates essentially relates the ideas of quantum mechanics or theories of quantum mechanics to reality. And by reality, I mean about, again, the act of measurement or doing a measurement. If you do a measurement, then you are going to get an answer. So here this postulate says that if you do a measurement with an operator A, which corresponds to an observable, some other observable, let's say small a, or anything else, if you operate it on the wave function, which contains all the information that is embedded that can be extracted of the system, then you can get many results. Now, these are essentially nothing but the eigenvalues, which are represented as small a1 and small a2. And these wave functions are called eigenstates, and the small a's are called the ai's or a1 and a2 and a, and they are called the eigenvalues. Now, these eigenvalues, since we relate it to an act of measurement, they have to be real numbers. They cannot be imaginary. And that is the reason why the operators of quantum mechanics are linear operators. Not only are they linear, they are Hermitian, because Hermitian operators always have real eigenvalues. Okay, so that is a very important point. Then we talked a little bit on the probability distribution, how to calculate means, and quantum mechanics provides you with a prescription of how to obtain a mean value, which is given here in the pink highlighted expression over here. It's an integral of psi star, and then the operator corresponding to the variable which you are going to measure and or of concern, and then the psi again, and integral over all space. And this equation basically allows you to find the average value of a quantity. And once you know psi, then you also know psi square, and then so you can essentially take a derivative of the curve and find out what the maximum is, and that will give you the most probable values. Okay, that is really what the prescriptions are. Then we talked about how, using simple mathematics of separating variables, we could separate out the time part and the space part, and under the special of the Schrodinger equation, or the time-dependent Schrodinger equation, and under the special circumstances where the potential energy operator becomes independent of time, which is true for many, many cases in chemistry and physics. You essentially get the special solutions of the form where the wave function is essentially a product of the space part and the time part. And once you do the separation of variables, you can find out that the time part is nothing but an exponentially e to the power minus I e t by h over h cross kind of a function that's always going to be there. Energy is embedded in there. And the space part, which we didn't do in which I just showed you this slide, kind of boils down very easily to the form of h psi equal to E psi, which is the standard time-independent Schrodinger equation, which is very commonly known in the chemistry community as the Schrodinger equation. Now, and this is, of course, used for calculations of electronic structure and energies and so on and so forth. Now, for a one-particle system, you can see that this Schrodinger equation is actually not really a simple differential equation, second-order differential equation. It's actually a partial differential equation with 3 variables. So it's actually pretty complex. So you can see that the more complex, more number of particles you take, more complex it will become. The partial differential equation will become more and more difficult to solve. Then finally, we discussed a little bit about wave function of something called stationary states. That is the idea that Bohr proposed much earlier. And we showed that if the potential is independent of time, then you can easily show that the probability density the probability is going to be independent of time. And so will be the energy. And this is the idea of having a stationary state. A stationary state is where the probability of finding a particle will be independent of time, it will not change with time. And the energies of those states are also going to be constant with time. However, that doesn't mean that the system is at rest. The system is really not at rest. It can be doing many things. But when I'm talking about measuring, getting the probability, you have to think of this hypothetical experiment where you are hypothetical experiment where you are doing the measurement of the position of the particle millions and billions and gazillions of times, and you generate your distribution, your probability distribution. That is independent of the motion of the particle, all right? So that's why the probability is independent of time. And then we finally said that, all right, if you have gone through this and if you have really not understood what I'm talking about, that is okay. Because most of the people still really don't understand what quantum mechanics is. The theory is actually pretty complicated in certain sense, philosophically. There are many other small intricacies. We are not really going too much into that. But what we're going to do today is try to see with a few examples, simple systems, how this theory spans out and how it can do certain predictions which can be verified using simple experiments, right? All right, I'm going to hold on here for a second and I'm going to check whether there are some comments here. The sound, some sort of echo is coming or disturbance is coming. Can anybody tell whether that is really true? Madam?
Yes, sir.
Is there an echo coming?
No, sir.
Okay, because there are some comments in the YouTube chat box which says that there's some background sound and echo comes. So,
Sir, our microphone is actually switched off.
okay. I don't hear anything, so I'm assuming everything is okay.
Yes, sir.
Hold on. Sorry, I need to just mute my phone. I'm getting this strange calls. Uh, okay. Now, what we're going to do today is start with a few simple systems. And the simplest of all systems that you can think about is having a particle in space, moving in space. So this particle is basically moving in space. There is no potential around. Okay? Now, the reason we start with this particular echo is coming. I'm not sure where is the echo coming from, because my is there echo coming?
No, sir. Maybe they may be having some network issues, I guess.
No, I don't think so. I think the YouTube. If you look at the YouTube channel, it says that there's a strong echo coming. So, shall I just mute my?
Sir, can you just wait a minute? I'll just check.
See, I muted the microphone actually.
So we can still hear you. Yeah. Right now it is muted.
Oh, sorry. The people in the who are watching through YouTube, they are getting some sort of a echo.
Sir, have you on your YouTube video?
What do you mean?
I mean, is your video also on? Audio of your video.
Yes.
So you have to make it at minimum volume. I think that's the sound the people are able to hear.
What you're talking about the YouTube, right?
Yes, sir.
No, YouTube is turned off completely. There's no sound.
It's turned off. Okay,
Yes,
sir.
yes. The other PC, there is no sound at all. So anyway, what I'm going to do is I'm just going to continue. See, because yesterday it was fine.
Yes, sir.
I'll try to probably talk slowly and see, because yesterday this was okay. Maybe I'll bring it closer. Maybe that will help. Is that better? Okay, they're saying that your madam, your voice is also reverberating. So maybe the way it is being sent to YouTube from Microsoft Meet Teams.
Yes, sir. I feel I need to contact to Purnima madam. Can you just wait for a minute?
No need. No need. I'll just continue. Ruchi is saying there's only a slight ego, so I'll just continue.
Yeah, sir. You continue and simultaneously I'll talk to madam.
Yes.
Yes.
Yes. Okay. All right. So we'll start with a simple system. And the simple system essentially is one particle which is moving freely in space. There is no potential, nothing. All right. Now, most students don't think that these things are very complex, but it's actually not very complex, because if you really look at the differential equation, it's not that complex. And the time now we are going to start only with the time independent Schrodinger equation, because we don't really care about the time part. Now you see that what I've done is I've written the time independent Schrodinger equation in the expanded form over here, and you see the moment we say that the potential and there's no potential, this Vx becomes 0. Okay, and so the equation becomes simplified. The Schrodinger just becomes the second order differential equation. Okay? And the second order differential equation, which is d2 psi x dx2, that is equal to E psi x, So that is the form of the equation. And people have known, mathematicians know this for a very long time, that a standard solution for this is in the form of a sin kx plus b cos kx.
And you see that you can verify this. You can see that if I take a derivative of this function as a solution on the side, you get back the same equation that we need. That is a differential equation. You can get it back. And here, this constant k comes out to be equal to 2me by h cross square. K squared is going to be 2me by h cross square. And that is because when you write it in the simplified form, you have to take into account these constants that are there, these Planck's constants. M is the mass of the particle, and E is the energy of that particular state or whatever. So those we represent in the form of k squared. Okay. Now, you can see here that I can simply rewrite energy, or this expression that I have over here, and find out that E is the energy of the system is nothing but k squared h cross squared over 2m. Okay, and here so far there is no restriction on this constant k. Okay, it was a sine kx plus b cos kx, so there's no restriction at all, and so energy has no restriction. This particle is moving freely in space. It can move around in with any energy. Any energy is allowed. There is no restriction of the energy. And the wave function will be obviously in the form of a sine root 2 me by h cross, because that is what k is, plus b cos root 2 me by h cross. All right. Now, there is often an idea that quantum mechanical systems will always have quantization. Okay. But most of our undergraduate students, as well as master students, do not realize where this quantization coming from. Okay, and I'm giving you a simple situation here of a free particle. And in this free particle, there is no quantization of energy, or there is no discretization of energy. And the best way to understand how this comes, how the quantization of energy comes in, is actually to try to restrict this particle in between two walls, or rather, if it's an electron, for instance, or a proton for a charged particle, we put it inside a potential barrier, an infinite potential barrier. So that is our next system. So if we put this particle, which is shown in the red blob over here, and if we confine the particle in a region given by between 0 and L, position 0 and L, then something strange happens. Now, we can clearly see that there are three clearly defined regions, and one is region 1 and region 3, where the particle cannot exist because the potential is infinite, and then there's region 2 where the potential is 0. So ideally, the particle should behave the same way as it would have behaved in the previous case of the free particle, right? That's what you would imagine in the region 0. But that doesn't happen. Something strange happens. Let's see how that happens. Now, the first thing that you need to remember is that there are these boundary conditions that we need to know. That is, at the boundary, that is at x equal to 0, the wave function has to vanish. We discussed about this in yesterday's lecture. Also, at x equal to L, the wave function has to vanish. Okay, these are two important conditions now that we have to restrict, our particle. That's how we restrict our particle. So this is very similar, as I told you, to the wave particle. So the wave function still remains the same, but since psi at 0 is equal to 0, all right, you can put the x equal to 0 over here, and so it becomes 0 is equal to a sine 0, because x is 0, plus b cos 0. But you know the sine 0 is 0, that's fine, but cos 0 is 1, okay? And that means if I have to keep the left-hand side equal to the right-hand side, the constant b has to be equal to 0. Okay, that is the logic. And therefore, you can see that I can write a0 will be equal to a sine kl, which is perfectly consistent, because the I'm sorry, this should be that is, so 0 is equal to a sine k, right? Now, where did I get this from? I'm getting this from the second boundary condition that I have, which is 0 equal to psi l. Why? Because if b is equal to 0, then the wave function boils down to psi x is equal to a sine kx. Now you can put at x equal to L, so psi L equal to 0, so 0 becomes a sine kl. So you get this new criteria that a sine kl equal to 0. So you see that this criteria, this thing that we have suddenly come up with, automatically boils down to this very neat effect that KL has to be n pi. Because if I have to have the criteria said that A sine KL equal to 0, that is only possible if K is an integral multiple of pi. That means suddenly a value, some n number comes in, and which we will call the quantum number, comes in, where n can only take values of 1, 2, 3, 4, etc., etc. And there's a reason why, of course, it cannot take 0, because the moment n takes 0, then other problems will happen. I'm going to come to that in one moment. And the other thing that you note is that in this particular derivation that I just did, A cannot be 0, because if both A and B are 0, then the entire wave function vanishes all over the space. So A cannot be 0. Therefore, A sine KL has to be equal to 0, and KL has to be equal to n pi. Now you can see that sudden imposition of these boundary conditions suddenly leads to quantization of energy, because we know that K is nothing but K square is nothing but it's defined as 2me by h cross square. All right. So you can now rewrite the expression for energy as n square h cross square by 8n square h square by 8ml square, where n is now the defined quantum number, which can take values of 1, 2, 3, 4, and so on and so forth. Now, you can see here what has happened. Suddenly, due to the imposition of the boundary conditions, I have suddenly gotten a quantization of energy. Now, the particle cannot any longer be present in any energy state. It can only take certain energies and not any random energy. That is a beauty that comes out of this restriction. Now, if you think about it, I can make this entire term h square by 8ml square for a given system with a given mass and given length of the box. And it boils down simply, the energy expression simply boils down to En is equal to, or energy of the nth state is equal to n squared beta. And n can take 1, 2, and 3. Now, I have written here as a subscript En. Previously I was only writing E in the case of the free particle, but here I'm writing En. And the reason I'm writing En here is because you can see here that the energy is going to be dependent on this quantum number n. Okay, and since this expression is like this, it's very easy to plot this data. You can plot the energies. You can see here that if I plot the energies in the vertical axis, and this is in terms of n squared beta, I'll get this different energy levels starting from 1 beta, 4 beta, 9 beta, 16 beta, 25 beta, so on and so forth. And so that means that as you are going higher and higher in the energy states, the energy gap between two consecutive levels are increasing. They are getting more and more spaced out. And this is the situation that happens in particle in an infinite potential well. Now, one interesting aspect of this is the idea of the 0-point energy. You can see here that the energy cannot take, n cannot be equal to 0. And n can only be equal to 1, 2, 3, 4, and so on. And so if you have, n equal to 1 as the least energy that's possible, this particle in a box predicts that there has to be a 0-point energy or a non-zero value of the minimum energy of the system that is possible. Okay. Now, this particular expression that I have over here, which can derive, has a very nice feature. And the nice feature is that this can be experimentally validated. If you can generate a system, which we're going to talk about much later, then today, then you can essentially predict what are the wavelengths of light that are going to be absorbed or emitted in this kind of a system. And not only that, you can even predict more things. You can see that this particular expression that we have derived using quantum mechanics tells you that as the mass of the system becomes larger and larger, the energy gaps become smaller and smaller. Okay, and that is essentially saying the same thing as when you have the system going towards from a quantum limit to a classical limit. Classical limit basically will have a larger mass, much larger mass. Then essentially the spacing between these energy levels will become shrink and they will become smaller and smaller and they will essentially vanish. And that makes sense because we would not expect to see such discretization of energy in macroscopic systems. Okay, so that's because the energy gap becomes too small for us to distinguish. But they are there, but they are very, 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 very small for us to distinguish. The second thing is that the idea that L square remains in the denominator, and L square is the length of this confinement where the particle is confined. So if the length is increased, that means if I do not really confine the particle, if the length becomes really, really large, again, the same thing happens. The energies again shrink together, the energy gap between two consecutive levels, they kind of disappear, which essentially is similar to the situation as if that we're looking at a free particle. Okay, that kind of a behavior. So that makes complete sense. Okay. So that is one of the great things about this very, 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 very simple system. Okay, now how do the wave functions look like? If you can look at the wave functions, you look at the wave functions, you will see that we had the format of the wave function as A sine kx. All right, A sine kx was the part of the wave functions because B was 0, so A sine kx is the wave function. K, we have derived what the expression for k is. Okay, so we can rewrite the expression of the wave function as 2 by L, which comes out as the normalization constant. I have not done the derivation here. You can easily do it. Sine n pi x over L. Okay. Now, so n pi x over L again means it's n is going from 1, 2, 3, 4, and so on and so forth. Now, once you see that the wave function is of this kind of a format, sine function, essentially it's like a sine function, is very easy to plot because we know how sine functions look like. Okay, so you can see here for n equal to 1, we'll have half of the part of a 0 to pi by 2 kind of a thing. Sorry, 0 to pi kind of a thing, half wavelength of a sine function. And then from n equal to 2, that's like a complete full wave. And n equal to 3, it is like 1.5 waves kind of thing of the sine function and so on and so forth. Now, this essentially means that we have now suddenly been able to find out the wave functions of a particle in a box, right, for a one-dimensional system. And so if it's true, then we should be able to find out everything about the system, right? Let's see how everything that can be extracted out of the system. Now, one of the things that is important here, which becomes relevant for you when you read up on hydrogen atom in your master's level, for instance, or even bachelor's level final year, is that the idea of nodes. You will see that the wave function changes sign sometimes. All right, at n equal to 1, it doesn't change sign. When at n equal to 2, it changes sign once. Okay, and the way it goes, so when the wave function changes signs, it crosses 0. That is what is defined as a node. Okay, this is a very wrong concept that people have, the students have, is that anywhere the wave function is 0 is not a node, is a node, but that is not true. And you can see here at x equal to 0 as well as at x equal to L, the wave function's value is 0, but those are not nodes. The wave functions have to change sign either from positive to negative or from negative to positive in order to call it a node. And so you see we can have a very simple relationship now of the number of nodes and the quantum number n. The number of nodes will always go as n minus 1. All right. The other interesting thing that comes out of the wave functions, which is often useful in spectroscopy, and I'm trying to relate this a little to Professor Anindya Dutta's talk, which comes in about symmetry, and that is that you'll see that the ground state wave function, if you imagine there is a mirror in between, right, is basically a symmetric function. It's an even function, and then the n equal to 2, that's like an odd function. N equal to 3 is an even function. N equal to 4 is an odd function. That means every alternate wave function is essentially going as even and odd and even and odd, right? So if you took a one-dimensional system, you can say it's like a mirror symmetry. If it's three-dimensional system. You can say it's a inversion symmetry or whatever, but please note that there are odd functions and even functions. Now, once you know the wave functions, you can always plot the probability density at least, because there is nothing but the square of the and here it's the dx is the volume element. So the probability is nothing but the probability density, the same thing here, because probability density is going to be at each point, and probability is going to be the distribution is going to be the curve. And so you can see that the probability of finding the particle in this region of space or n equal to 1, 2, 3, 4, etc., does not remain the same. That is very, very important to understand. That means if the particle is in the quantum state 1, n equal to 1, then there is a particular distribution of the probability. If the particle is n equal to 2, then there is a different distribution of probability. If it's n equal to 3, 4, there's a different distribution of probability. And these are characteristic of the states or the eigenstates that these particles are in. Okay, so the idea is that this particle in this confined infinite potential has these different eigenstates, energy states. Okay, they are well defined. Now remember, I'm talking about these eigenfunctions and eigenstates. So these functions, this psi1, psi2, psi3, they are the eigenfunctions of the Hamiltonian operator or the total energy operator. Why? Because you can see that if I do a measurement on the system, if the system is in n equal to 1 or n equal to 2, if I do a measurement of the system and I find out that the system is in n equal to 1, all repeated measurements will give me the same value of energy. That is going to be 1 beta. Okay, if I do a measurement again and find the system is in n equal to 4, okay, then all consequent experiments that I do independent of time, the system will remain in the n equal to 4 state, which has an energy of n equal to 16 beta, or energy equal to 16 beta. And so you see, repeated measurements on the system will lead to the same answer, and this is a real number. This number 16 is the real, or 16 beta is the real number, which is nothing but the eigenvalue. Okay, so that's how I can relate to what I was saying yesterday about the eigenvalues, right, and the eigenfunctions and eigenvalues. Now, the other thing interesting to know that the particle is probably moving around, right? I mean, I don't even really know whether the particle is moving around or not. I'm going to come to that in a second. But very often, a question comes in to us is that, okay, n equal to 1 state, eigenstate, which is shown here at the lower bottom. I can totally understand is the probability is maximum in the center of this potential well in this region. However, if you look at n equal to 2, it's very strange. It seems that the probabilities, they have equal probability of finding the particle at n equal to L over 0.25 L as well as 0.75 L, right? And it's more funny, it's more strange that the probability of finding the particle at L equal to 0.5 L or half L is 0. Now, what does that mean? I mean, do we have two particles on two sides of this box and nothing in the center? If the probability of finding the particle is 0 at the center, then students get confused. Why? How does particle move from one point to the other? One side to the other. Then that's kind of counterintuitive and kind of weird. But if you remember my yesterday's lecture as well as my first few minutes of what I discussed today, this particle is not really a particle. Okay, that's why I don't call it PIB at the top. I call it WIB because this particle is actually a wave vehicle. Okay, so it's very easy to understand if you think of this particle as a wave, because if you take a rubber band and attach two sides of with your fingers and ask your friend to pull it from the center, right? You can see the wave, the standing waves that are formed, right? That's a picture that I've shown here on the top. And the standing waves, they have amplitude on one side, they will have more amplitude, on the other side they have less, but then suddenly they switch, right? amplitudes change. This side becomes more, and then this side becomes more, and this side becomes more, and so on, right? So if you think of this particle as a wave, there's absolutely no problem understanding why the probability distribution can be like this. Because, as I told you earlier, we cannot ask the question, or quantum mechanics doesn't allow you to ask the question, how is the particle moving from one side to the other? Because if you have seen the video that I sent, video clip by Feynman, he tells you that you cannot, this is an invalid question. You cannot ask this question. Quantum mechanics is unable to say because these are quantum particles. So they may or may not even exist. They may pop out of nowhere and they may disappear after the measurements. We don't really know. But all we can say is, okay, if we do many measurements, what will be the distribution of my positions of finding the particle? That is what we can find out. Okay, we cannot discuss, or we cannot say how the particle is moving from one end to the other end, or how it's going around, because this is not a classical Newtonian particle. This is a quantum particle. So there is this kind of question doesn't arise. Okay. Now this link also, this idea also links to the fact that if you notice that the position, right? If you take the position operator, which is nothing but x, right? And if you apply this to this wave function, so it will be x times sine, right? You don't get an eigenvalue equation. Because if the position operator operates on this, you get a product which will be root over 2 over L times x times s sine n by x by L, right? So that's not getting the same function back. So that tells you that for the position operator, this function is not an eigenfunction. What that means essentially is that if you do a repeated measurement on the position of the particle, you are never going to get the same position every time. And the same is true for momentum as well. You can easily see that if I take a momentum operator is a derivative operator, ddx operator. So if I take a derivative of sine, which we did an example yesterday, we are going to get a cos function, right? So you're going to get a different function. So that means if you do a measurement of the positions as well as the momentum many times, you are not going to get the same answer. You are going to get different answers. Okay. So whenever these kind of situations happen, when you do a measurement, you get a different answer from the next measurement or the previous measurement, then you cannot use this eigenvalue equation anymore. What you have to now do is, because these are no longer eigenstates, this wave function is no longer eigenstates of the operator that you have chosen or the observable that you want to measure. So under those circumstances, what you have to do is, I'm sorry, I should have switched slides. I forgot to switch slides. Under those circumstances, what you really have to do is you have to calculate the average values and the most probable values, okay, of the particular variable. But here you can see that it's true for position. It's easy to see in the space position. You can find the average value and the most probable value very easily. We are going to do a small tutorial on that soon. In contrast, energies you can see are very well defined, right? Energies are very well defined. So if you do repeated measurements of energies, you are going to get, every time you are going to get the same eigenvalue of energy. All right. Now, one thing that I should mention here is that one of the very fun things that comes out, and let's not go into the details of that, is that if you have these multiple states of an eigenfunction, and here the eigenfunction, the wave function of one particle in a box is an eigenfunction of the Hamiltonian operator. Now, all different eigenfunctions of operator are orthogonal to each other or orthonormal to each other, and that is represented by this. That basically means that if you take a product of n equal to 1 and n equal to 2, and if you do an integral over all space, you are going to get 0. That's what the definition of orthogonal means. And if you take the same guy and if you do a product with itself, that is what is called, that you are always going to get 1, because the probability of finding the particle in each state has to be equal to 1 over all space. Okay. So whether the particle is in n equal to 1 or 2 or 3 or 4, it doesn't matter. In each of these states, the wave functions, the probability of finding the particle has to be equal to 1. And this orthogonal condition is important, as we will see later. It will become important, But let's not worry about this too much. I've given you guys in the tutorial sheet that is provided. I have given you. I do not know where the tutorial sheet is. Yes, in the tutorial problems number, it's in that Google Drive folder. I think problem number 10, problem number 10 is one where, you can essentially do a little bit of math and a little bit of picture drawing, graphical plotting, and you can actually figure out that they are actually orthogonal. It's very easy to do, but it's a good exercise to do that. So the point is that, when you are not, when do not have eigenfunctions, then you have to take average value. So this is the prescription, as I told you, for to calculate the average value. And so let us do a small exercise before we move on. Let us try to find out what is the average value of the position. Right now, you can see the answer. You can see the answer from this. Well, it's not that easy to see, but let's see what it comes out. If you use this expression that is shown here at the bottom, just one moment. Now, can everybody see the entire screen, madam?
Yes, sir.
Can you see the entire screen?
Yes, sir.
Because the bottom part in my computer is getting kind of.
Yes, sir. Yes, sir. So it is not visible actually. The last line.
Last line. Okay. So for those who cannot see this last line here, let me help you a little bit and redo this in a way so that everybody can see it. That is very strange because. Okay. So there's the equation that I had. We all already know this is the prescription that was given to us by the postulates of quantum mechanics to calculate the average value, right? So let's do that. If we want to calculate the average value of the position, right? Then what do we have to do? We have to take the integral of psi star, and then you have to take the operator for position, which is nothing but x, and then we have to take the psi again, and then multiply it with dx, and then integral over all space. And if you do the math turns out to be, because you know the wave functions already, will come out to be something like this. Now, can you guess what is going to be the answer? The average value. You will see that the average value, okay, will always come out to be L over 2. Okay, no matter what state it is in, it is going to be constant. The average is always going to be back in the middle. That is what the average. Average is, you can see here, is not always a good representation where the particle can be found. Because for n equal to 1, yes, it is true, at L over 2, you have a highest probability of finding the particle. But for n equal to 2 or n equal to 4, that is not true. Okay, that is where the minimum of the probability of finding a particle is, isn't it? So this is just to give you an idea that average is not necessarily the only parameter that you need to extract. Sometimes you need to extract the most probable value as well in order to get an idea of what's going on. You can do the same exercise for the momentum. Right now, I've done it for you, where if you want to find the average value of momentum, you can see what is going to come out to be. If you do the math, this is the derivative, you put the value of psi, sine becomes cos, so you have an integral of 0 to L of sine n pi x by L times cos n pi x by L. And those who are good at math, okay, then can easily figure out that the answer to this integral, or this definite integral, average value, is going to be nothing but 0. Again, it can be understood very simply that particles can essentially have momentum with which they can move towards this left-right direction or to the right side direction. But again, I really don't want to give this description. Remember what I said yesterday, that we are using this analogy and contrast. I'm giving an analogy to Newtonian particles, okay? But the real picture may be completely different, which I really don't know. But I am giving an analogy, and this analogy may or may not be correct. Okay, this is something that you have to understand, that it may or may not be correct. But this is what I would give, because in a macroscopic world, that is what I would imagine, that particle can go this direction or this direction. So will have opposites. It's a vector, so it'll go in two different directions. The average will come out to 0. Okay. Now, I do not know why we are unable to see the entire screen. Madam?
Yes, sir.
What I'm going to do is I'm going to stop sharing, and I'm going to restart the sharing. Okay, let's see whether that helps.
Okay.
Because before it was okay, right?
Khalida, because I'm not on the YouTube, I'm on the Teams, so that's why. Khalida?
I think same problem is happening in Teams.
Ma'am, we are not able to see the last line in the YouTube also.
Okay.
Somewhere at the beginning today or somewhere in the middle?
Khalida, from beginning you're not able to see?
Yes, ma'am.
You should have pointed it
Sir
out.
just reported me, Pusalkar sir just reported me that it is not visible, last equation.
So you should have told me, because I didn't realize this. And so what I'll do is I will again try to recast it and see whether that helps. Okay. Because yesterday it was coming out to be fine, right? Okay, now what? Now it's okay for this situation, but if I do full screen, then what happens? You know, this is because the screen is, my screen is different. Maybe that's why. Can you see? No. Madam?
Yes, sir.
I do not know what is going on, but somehow the format of my, the thing is not coming out to be right. The projection, I do not know why this is happening. So,
Purnima?
Because maybe because we are sharing it is in full screen.
Excuse me? Can you say that again?
This is because we are sharing the slides now, because the screen is in full screen.
Yes.
The mode is in full screen.
I am in full
screen. From our side it is on full screen.
I know.
We are,
yesterday this problem didn't happen, I said.
Yesterday it was not there, I think.
Yesterday there's the same file, so that's why I'm not getting why it is creating this strange problem.
Suppose you don't do slideshow and just show it, would it be better?
Okay, probably I will do that if for important equations. But there are some. Okay, hold on. Let's see. He's saying that yesterday was also, many of the students are saying yesterday there was the same problem. So
but nobody reported it yesterday.
Yes, nobody reported it, so I didn't realize it. I'm really sorry about that, but let's see. Let's try to do that. Okay. 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 So let's just move on. We will see. Now, the other thing that is important for us to understand is, okay, what is the probability of finding a particle between any 2 points, right? And this is another thing that sometimes people get confused, because so far, whenever we have calculated the probabilities, we have tried to find out, the limits have always been like, all space kind of thing. But when you want to say that I want to find what is the probability of finding electron between an interval, then you have to change your integral limits of your integral, right? So now if it's between x1 and x2, you have to use the same expression as the probability, but then you have to put the different limits and do the calculations. And once you do the calculations, you'll be able to get an answer, which should be consistent with the picture that is shown here on the top right, because you can see here in the top right, it tells you that at n equal to 1, the center will have L by 2 position will have the maximum probability. Whereas in n equal to 2, the center will of L over 2 position, x equal to L over 2 will have the minimum probability, or probability will be 0. So if you do the math and if you do not see you are getting this consistent answer, in fact, it's far more easier to just draw pictures and find out what the probabilities are rather than actually trying to calculate the values. But sometimes you have to do these calculations to get some numbers out. But the good thing about this is that this technique is that these quantum mechanics prescriptions that are provided can let you predict real numbers, which can be, again, related to experiments. Okay? All right. So this is what my take is on what is the essence of quantum mechanics. Again, I'm probably, have to move things up here a little bit because this is not visible clearly. And I'm not sure why it's not visible today. So this is what I would call as essence of quantum mechanics. Okay. So what we learned is that particles and waves are not separate or distinct entities. We cannot precisely determine, the positions or the velocities, etc. But the wave function provides all possible information of the system. And as we saw from this example of particle confined in a one-dimensional potential well, infinite well, we can extract average values and probabilities for the classical variables. We did that as an example for position as well as for momentum. But we had to use these operators, right, for the classical variables. And most importantly, the discretization of energy only, or for, later we'll see for hydrogen atom, when you read hydrogen atom, you will see that even angular momentum will be discretized. This doesn't come just like that. It comes spontaneously due to restriction of the wave function. Only when you restrict the wave function or you impose the boundary conditions, which we did today as an example, we said x at x equal to 0, wave function is 0, at x equal to at L, wave function is 0. When we put those restrictions, when we put those boundary conditions, that is when the discretization of energy, or later you'll see angular momentum, also comes in. That means without putting in boundary conditions, we can never have any discretization of energy or any quantization of energy. Okay. Now, the other important thing to notice is that quantum mechanics does not violate classical mechanics. And we saw that as an example for large mass, it kind of boils down to what would be predicted by classical mechanics, right? So, which is a good thing because you cannot be inconsistent with classical mechanics. And the reason why these predictions, the quantum mechanics has the ability to do some predictions which can be experimentally verified. Right? And the reason why quantum mechanics is still out there and why people believe that quantum mechanics is inherent uncertainty of the small particles and this electrons and protons and molecules. Its inherent uncertainty is uh, it's inherent of nature. It's a very strange but characteristic of nature for this microscopic quantum particles. Um, is because experiments have proved the or verified the predictions of quantum mechanics, and quantum mechanics have almost never failed to do to predict certain things in an incorrect fashion, and experiments validate its predictions. So that is one of the most important things that we have in terms of understanding this. Okay, so what I'll do is I will now take some questions before we move on to the next session, which will be a little bit more application oriented. We'll soon see that. Okay, so Khalida ma'am, do you have any questions from Microsoft Teams?
No, sir.
Okay. Hold on. Let me see whether I have some questions from here. All right. It was not seen yesterday. Problem from the beginning. Okay. Questions. Without slides to the presentation, just zoom in. It might help. Okay. I can do that. Yesterday problem was there. I'm looking at slides from different device. Okay. All right. Do you have any questions from the students? I know it's been a long session. The first section was pretty long, but I did a little bit of 15 minutes of recap. So I thought that it would help you guys refresh what we did yesterday. Okay, do you have any questions? I'm going to give it a little bit of time for everyone to okay, we have one question already from Chandan Kumar Sahu. What are the size scales of L for particles behave classically for different values of n? Okay, now there is no real number that I can predict to you here, but it's typically in the order of maybe few tens of nanometers, right? Or tens of nanometers, okay? If you go beyond several tens of or beyond hundreds of nanometers for a quantum particle which is much smaller, let's say one sub nanometer in size, then because a quantum particle can also be an atom, can be a hydrogen atom, can be a quantum particle, for instance, right? Or it can be a molecule. It can be in the same way. So typically, you can do a calculation. You can do a simple calculation and see. But what you really mean classical? In order to get the classical limit, you probably have to increase length to probably beyond hundreds of nanometers. All right. So that's really what it would be. But it's a continuous thing. Okay. All right. Saurabh Banerjee, would you please explain the solution of psi equal A sin kx plus B cos kx? Why not any other trial solution? Okay, yeah, you can have other trial solutions. If you look in books, you will find out that you can. This is one of the solutions. But it's actually probably not the most general solution. The most general solution, I think, is in the form of e to the power ikx plus e to the power minus ikx kind of a format. Okay, but that will exponential ikx will also boil down to a sin x plus cos x kind of a format. So they are not really contradictory. But there are other solutions. There are other solutions that you can have. But generally, these are considered to be the most general solutions. Okay, and this is known from mathematics for a long period of time. This is known that for an equation, a differential equation like this is one of the very commonly used solutions. That's why we have used these as solutions. Can we then we have Yashaswini Gupta has a question. Can we say that eigenvalues physically correspond to the actual value of the operator used in the equation? Okay. Now, Yashaswini, the operators don't really have any values. Okay, the operators correspond to a observable. Like for instance, you have a momentum operator, which is unobservable. I can measure the momentum, right? I can have an operator for the energy, kinetic energy. I can measure the kinetic energy. I can have an operator for the potential energy. I can measure the potential energy. I can have an operator for the total energy. I can measure the total energy. Now, uh, the what you observe, eigenvalues, right? These are going to be the actually observed values for the observable, not the operator. Okay, the operator is just a representation of the action taken to do the measurement on the observable. Okay, so what you're measuring as eigenvalues, what you're getting as eigenvalues are actually the values, the real values that would be obtained upon measurement of the observable. Okay, now that's Ashwini Gupta. Then we have Sagar Kadam. What happens? The particle goes in infinite potential. The particle cannot go in the infinite potential, Sagar, because it just is going to be restricted. It's infinite potential, so it can never go there. Therefore, the wave function value over there is going to be 0. Suranjana Dan asks a question in Heisenberg's uncertainty principle. There's relation between uncertainty of position and momentum. And similarly, we got energy and time, and they are called to be conjugation. Can you elaborate? I actually do not want to elaborate this at this moment, but you can read up on books a little bit, because you see that the idea that momentum and position are it's not conjugation, it's conjugate variables, I think, is that the relationship for momentum and space or position, uh, they are related by this uncertainty principle, and then there's a relationship between that you can derive from otherwise, which is time and energy. You can derive the same thing. Now, I do not really remember what is the root use of the word conjugate variables. Okay, but essentially it implies that there is something to do with some transformation can take you from one to the other. There's some sort of equivalence of some sorts. Okay, that is what is probably what it means. But I don't want to go into the derivations and other things right now. Ayush asked, what is gravity? I have no idea. I have no clue what is gravity, but it is some sort of, to my understanding, it's nothing to do with quantum mechanics, and at least now, unless you're in a black hole, which is a singularity, and there's a curvature. Gravity is a curvature of space-time. Okay, let's not get into that right now. Okay, Rishik has asked, is it true that the limit h goes to 0? Predictions of quantum mechanics are the same predictions as classical mechanics. Again, I don't want to get into this right now, because there are very nice books on, there's a nice book, I've forgotten the name of the book, but if age becomes 0, many weird things will happen. Okay, now the age becomes large, again many weird things will happen. So the thing is that H, the idea that H is such a small number, it's 10 to the minus 34, right, Joule sec, that essentially makes this quantum behavior like they are. Okay, so the quantum behavior is effectively some sort of a consequence of the entire theory is a consequence of this H being so small but not zero. But if you make it zero, then something else will happen. Now, what will happen? I don't want to say. I don't want to comment right now. Again, Ayush, what is gravity? I told you I do not know what gravity is. Do you teach quantum mechanics by matrix way? No, I don't. Heisenberg's formalism is the matrix way. We do in the higher level, master's level, but not here. I think Ayush needs to be told that this is not a talk on gravity. Okay, there is a question by Aparna Shukla. We assume that boundary conditions for simple systems, linear molecules that is 0 to L. But what about complex systems? It's a question by Aparna Shukla. It's a valid question. So you see that boundary conditions will automatically come in. So when you have a one-dimensional system, the boundary conditions, as you correctly said, is easy to define. But complex system is not necessarily means a three-dimensional system. A complex system is simply, for instance, let's say hydrogen atom. When you do hydrogen atom, you will find that you have to deal with a different kind of coordinate system, which is going to be like r theta phi coordinate system, which is the spherical polar coordinate system. And there they have different boundary conditions. They do not have the same boundary conditions as 0 to L. There will be boundary conditions from 0 to infinity. There will be one boundary condition which will be 0 to 1 and 0 to pi. Another one boundary condition will be actually those are the limits, not the boundary conditions. Will be where the wave function has to be the same at a value of one angle and a value of the same angle plus 2 pi angle. Or things like that. So there are different boundary conditions that you can obtain by intuitively understanding what the system is. Okay, so it is actually not that complex as you think it's going to be in reality. Dhriti Sanjay asked, what is the best book if you want to study more about quantum mechanics? I have already suggested a few books. If you please go back and look at the Google Drive folder, I provided you with some references, some books over there. I think I did. Let me check. Just one moment. Just one moment. Let me just quickly check whether I mentioned it here or not. I think I did, but maybe I didn't. Yes, I didn't do it here. I did it in the very first, yeah, second slide. If you can see my second slide, I have mentioned 4 books here. These are very nice books, and I particularly like Levine. I particularly like both Levine and Engel and Reed, physical chemistry books, which are at the undergraduate level books. Macquarie and Simon is also good, but Engel and Reed is very good. Levine is also I like a lot to read and understand. Okay, hold on, please. Okay. All right. Now, next question is that okay, Fourier transform. Yes, I don't. Okay, Suranjana Dam has asked about Fourier transformation. Yes, I don't want to get into this right now at the undergraduate level. So, yeah, I won't answer that question. Okay, is the chem class? What is going on? Okay, there's no question. Okay, there's a question by Shrudeepa. How discretization of energy arises due to restriction of the wave function? Actually, Shrudeepa, this is what I just showed today. That how discretization of the wave function leads to Hold on. So, Sudeepa, this is what we discussed today. We showed you how when we impose the boundary conditions, this quantum number n automatically came in. You see that previously the k was this constant that we chose arbitrarily, which had no restriction. You can see here on the left, there's no restriction on k, but when we impose the boundary conditions over here, you can see that there's suddenly this quantum number n comes in, and this n comes in because we put at psi l equal to 0, and therefore a sine kl must be equal to 0. That is how we got the relationship that kl has to be equal to n pi, and n became the quantum number. And that allowed you to allowed the energy to be expressed in terms of n. And since n can only take certain values, automatically you have discretization of energy. Okay, so that is what the answer is. You get discretization of energy owing to the imposition of the boundary conditions and nothing else. Okay, now this was Sudeepa H. All right. Then we have, is there a physical relationship between pairs of complementary variable? I do not know whether there is any physical relationship between them or not. It's a question by Pavitra Parthima. All right. Then tell us something about your research work, please. No, this talk is nothing to do with my research talk, so I'm not going to tell you much except for maybe one slide. At the very end, when we talk about applications of particles in a box, I'm going to show you one slide, which is related to my research work. Why n in the energy of particle is not taken zero value? I actually didn't want to answer this question, but if you think about it, if n becomes 0, right, then what happens to the wave function? Think about it. If you think about what the wave function is, right? If n becomes 0, what happens to the wave function? Does it exist? Think about it. So that automatically tells you that n cannot be 0. Okay, n has to be a non-zero value because the wave function cannot disappear. If the wave function disappears, then the particle doesn't exist anywhere in the universe, which is not possible. So you have to think in this kind of a fashion. I didn't want to answer this. I thought I'll ask you this question later, but anyway, good that you asked. All right, this is a question by Girish Pusalkar. The next question is by next problem. I'm sorry, that's not a question. Oh, okay. Ankita Nath has already given the answer, and thank you, Ankita. Very nice of you to give the answer for me. I should not have spoken. Aditi Pradhan is question from Aditi Pradhan. Do wave functions with higher n, in particular in a box, correspond to the classical state? Not really. I mean, it doesn't really correspond to the classical state because you're still a quantum system, right? I mean, but if you go to extremely high values of n, what is going to happen is that all these fluctuations, you can see, if you look at the slide that is open here, you will see that the number of these oscillations are going up, right? So the number is going to become so many of them that it will become very, very small, like this. So the particle will basically have almost the same probability over the entire box. Okay, so that particle is spread out over the entire box. Okay, now so that's what's going to happen, right? Now, before I move on to the next question, I want to pose a question. I want Ankita and Girish Pusalkar, all right? You guys, please remind me of the n equal to 0 thing, all right? I have to discuss something. Before I move on to the applications, more realistic stuff. Okay. Do wave function with higher n and okay, done. Then we have a question from Udita. Udita, how can we get sufficient number of intensity measurements for a complex vector reconstruction in quantum tomography? Udita, I have no idea. As I told you, I'm not really an expert in all these things. I teach. I do teach. I am not a practicing quantum mechanics person. You have to ask somebody whose knowledge is better than me on that. All right, far better than me. Um, you know, you can find out. You can probably find out from doing a Google search of how that is done. Is quantum mechanics applicable for hydrogen atoms? Is a question by Nachiket DM. Is quantum mechanics applicable only for hydrogen-like atoms? Can we apply for other atoms? Of course, we can apply for other atoms. It can be applied for many different complex systems. That's why it's so powerful. Then we have a question, feedback link. Please send votes for that is different. Okay. Aditi Pradhan, continuing from the previous question of higher and corresponding to classical observations, shouldn't the energy levels be more closer as n increases that we get continuous energy? Okay, Aditi has asked me the question now related to the classical limit question. No, the answer is actually the opposite. If you look, Aditi, in the energy levels, which is shown in the previous slide, the energy gap between the levels is actually increasing. With higher value of n, the energy gap is actually increasing. It's not going down. Okay. So what happens in a harmonic or an harmonic oscillator for a vibrating molecule, and harmonic oscillator, as you the potential curve is like this from your side, right? As you go higher energy, the energies become closer and closer and closer. But here, the energies are getting more and more separated from each other. So what we're saying is exactly opposite of what happens. So we will never get continuous energy for a particle in a box if you go for higher n. This is true only for an anharmonic oscillator where you have a simple diatomic molecule which is vibrating anharmonically, and then the potential is anharmonic. That is when you are going to get what you're saying. All right, I think we have got enough questions. So let's go back to the question that I was asking that's related to Ankita and Girish. Now, let me pose a question for you guys. Okay, you guys can all see this. Okay. So the question is, does 0 point energy has to exist for all quantum mechanical systems? Again, to rephrase the question, what I'm asking is that, can there be a quantum mechanical system where the minimum energy is zero? Is there a conflict? Because this is a question that often students have, that how can the minimum energy be zero? So the question is, can the minimum energy of any quantum mechanical system, right, system be zero? And yes, we have already got some nice answers. Oh, which has been retracted. Vaishnav Shah gave an answer which has been retracted now, but he gave a correct answer. Prahlad Shanoy says yes. Prahlad Shanoy, rotational, absolutely. So you can think of, instead of particle in a box, and I want you guys to, I don't know, can I share YouTube thing here? Let's see whether I can. If you take a particle in a ring, okay, and if you do a YouTube on particle in a ring, you will find out that, okay, let's not forget about it. If a particle is moving in a ring, okay, that equation boils down to something like this. Okay, I will Okay, so YouTube, Chrome tab. Okay, let's see. Let's see whether you guys can see this. Can you see that? Yeah. The particle in a ring. You'll see the in this particle in a ring problem. Uh, the differential equation, the Schrodinger equation, boils down to something like this. Okay, h square over 2m r square, d2 side d phi 2, where phi is the angle, and that is equal to e phi, e sine. And if you solve it, and this is how the wave function looks like. If you solve it, you will find out that you are going to get quantum numbers after imposition of the boundary conditions, where the quantum numbers can take n equal to or m equal to 0 value. And once you put the values in for m equal to 0, the energy will come out to be 0. So the question that I am asking to you guys is that under a situation like this, when you have a particle in a ring, and I'm not going to answer the question now, I want to think about it. Does this n equal to, or the quantum number equal to 0, or the minimum energy state being 0, does it violate the uncertainty principle, okay, for a particle in a ring? Okay, so this is something that intrigues a lot of students. I have had many questions coming from even very senior students on this particular aspect, and I want you guys to think about it, because that is something that is worth thinking about. Okay, we already have some answers. Um, so Seem Sabut Sarkar has said that there must be a minimum energy in every quantum mechanical system because the Planck's equation depends on n plus half. So that is for the vibrational state, not for the rotational state. As correctly pointed out here, for a purely rotational state, as Prahlad Shenoy has pointed out, that is, and as well as Nachiket has pointed out, uh, that for purely rotational state, minimum energy can indeed be 0. So I want you guys to think about it, and you can put your answers. You can uh, WhatsApp me your answers. I have already given you my number, WhatsApp numbers. You can give the WhatsApp me your answers, and then uh, I can tell you, or by the end of this lecture, I can tell you as well. We have about an hour left. Okay, so what I'm going to do now is I'm going to switch to a little bit of more complex situations. And once we do that, again, we are having the same problem. I think if I project it, can you guys see my
Yes, sir.
it's getting cut off. The lowest part is getting cut off, but I don't think I have a choice right now. So I'll just continue like this, all right? Okay. You know what? I am going to take a couple of minutes break. Okay. 1 minute break. I'll come from the bathroom. Is that okay, everyone? Madam?
Yes, sir. It's fine.
Yeah, I'll just come back in one minute.
Yes, sir.
I'll leave this slide open so that people can just go through this. Oops. Okay, I'll be back in a minute or two.
Hello.
All right, I'm back. So what we're going to do now is get to the next level of complexity. And the next level of complexity involves a particle in a 2D world. Okay. Now, you can see here, if I have this potential well, infinite potential well, instead of one dimension, it is two-dimensional, then situation becomes a little bit more complex, because now the wave function again will now not only be a function of only one dimension, that is x, but it will also be a function of x and y, right? X and y. So under these circumstances, situation will become this. The solving the Schrodinger equation will become a little bit more complicated. Now, the reason we have chosen this particle in a 2D well is actually because inside the well, the potential is zero, which makes our life simpler. And how does it make your life simpler? That is because you can see that the kinetic energy parts of the Hamiltonian, which is given by the second derivative with respect to x and the second derivative with respect to y, they are additive terms, right? So essentially, what that means is that the Hamiltonian of this two-dimensional system can be written as a additive or addition of Hamiltonians of two one-dimensional systems, right? And this is particularly useful because under these conditions, where you can write the Hamiltonian operator as a sum of Hamiltonian operators, each belonging to one dimension, in this case x and y, then again you can write, or you can get this solution wave function, or the solution to the differential equation, or the wave function. You can write it as a product of two wave functions, where each of the wave functions are a part of one variable, as shown over here. You can see that psi x product psi y, and in one dimension, we have already solved what the wave functions are going to be. We already know what the wave functions are going to be in one dimension. So essentially, for such a system, you can write your wave function as root over 2 over Lx and sine nx by x by Lx product root 2 over Ly, because Lx and Ly are not necessarily the same. And then sine ny pi y over Ly. And if you'll notice very carefully here, we have nx and ny here. Now there are two quantum numbers. Each dimension, for each dimension, we have one quantum number. And that is understandable, because you can have confinement both in nx as well, in x direction as well, and in y direction. So you will have two different quantum numbers corresponding to the two different variables that are there, right? And if you look at the calculation of the energies, it becomes very, very simple. You can see that energies, because the wave functions are going to be eigenfunctions or eigenstates of the Hamiltonian operator, right? You can see that the total energy of the system will just turn out to be addition of the individual energies in one dimension, okay, which is given as the EE subscript nx and E subscript ny for x and y dimensions respectively, right? So that's how it turns out to be, which again makes our life simple, because we can then straight away write down what the energy expression is going to be for a two-dimensional system, such as a wave vehicle in a 2D potential well. Now, this thing that I just showed you, that when psi is when the Hamiltonian can be separated in parts, each containing one variable, right? Then psi can be written as a product of each wave function, right? Of several wave functions, each of one variable. And energy turns out to be the sum of the individual energies of those things. This concept is actually a very important or very vital concept. This will come in again and again when you read quantum mechanics, when you read on hydrogen atom. This is going to come in. everywhere it is going to come. Okay, so this is something that is really vital, and this is something that we learn from potential of 2D well. Now let's go back and look at what the energies look like. All right. So in a 2D well, where Lx is not equal to Ly, you can see that I'll just have to write down as in terms of, I can't write the same beta anymore because Lx and Ly are not the same. But we can now define a new beta called h squared by 8m as beta prime or something like that. So this is a constant for a given system. M is the mass of the particle that is in there. H is the Planck's constant. And now we have nx squared over Lx squared plus ny squared over Ly squared. And again, nx and Ly can again go from 1, 2, 3, 4, and so on. There are these two different quantum numbers that are part of this that are due to these two different dimensions, right, that are present in the system. And if you make this box such that Lx becomes Ly, okay, you can see that the denominator becomes the same. So now we essentially can retrieve back our old beta, which was h squared by 8ml squared. That is the old beta that we had before. But instead of the energies being just a function of that beta times n squared, now it's going to be beta times nx squared plus ny squared, right? And nx and ny again can go from 1, 2, 3, 4, and so on and so forth. Now, I have given a tutorial problem to you to calculate energies for 2D system, which is easy to do because you know that nx and ny can take these values only and nothing else. So these two quantum numbers, if you can plug in any two quantum numbers, you can define the state of the system. You can find out what the energies are going to be. And for instance, if you take a square box, right, or if you take a rectangular box, which is shown over here on the right side, you can see that there's going to be these energies that are there, right, which are going to correspond to the quantum numbers nx equal to 1, ny equal to 1, nx equal to 2, ny equal to 2, nx equal to 3, ny equal to 3, and so on and so forth, right? I mean, you are going to get different values. Why? Because you're going to get, depending on the length of the box, right, of Lx and Ly, these energy levels are, the ordering of the energy levels are going to change, right? Now, a very interesting thing happens when Lx and Ly becomes the same. If the length becomes the same, it becomes a square box, right? You will notice from this expression here itself that for two different states, that is, for nx equal to 2, let's say nx equal to 2 and ny equal to 1, the energy is going to be 2 squared is 4, 4 plus 1, 5, 5 beta. And for another state, given by nx equal to 1 and ny equal to 2, that is also going to have, that's a different wave function. Remember, it's a different wave function because your wave function is this. So in the first one that I just told you, this will be sine 2 pi x by L and sine pi y by L. And in the second one, we will have sine pi by pi x by L, and then we will be and product sine 2 pi y by L. So the product wave functions are different. For these two wave functions, you end up getting the same energies because nx squared plus ny squared turns out to be 5 for both the cases. Okay. So these are basically what is called degeneracies. That means you have two different states. The wave functions are different, but the energies turn out to be the same. Okay. And you will notice that for a square box like this, the 1, 1 is going to be singly degenerate. That means you are only going to have one energy level. But the moment you go to the 1, 2, and 2, 1 states, nx equal to 2 and ny equal to 1, and nx equal to 1 and ny equal to 2 states, you are actually have two energy levels of the same energy. And again, you will see the same thing happening for the nx equal to 2, ny equal to 3, and nx equal to 3, and nx equal to 3, and ny equal to 2 state. The same thing will recur. And so this tells you something very interesting, and that is that this degeneracy, which is the having similar or same energy levels, that is actually some sort of a manifestation of the symmetry of the system. Okay, again, I'm relating to symmetry here because Anindya Datta is talking to you about symmetry, and so I thought that it's important for us to relate some aspects of symmetry, and you will see in his lectures that symmetry and quantum mechanics they are intricately intertwined with each other. Okay, they're very symmetry is extremely important for quantum understanding quantum mechanics, and quantum mechanics is very useful for symmetry is useful for solving quantum mechanical problems. Now, one other thing that I'd like to mention here is that this also has some practical aspects. This idea that something which is more symmetric will have more degeneracy, and that you can see in your inorganic chemistry classes when we talk about crystal field splitting. Okay, more symmetric systems will have more degeneracy, and the degeneracy is lifted if you remove the symmetry of the system. For instance, in octahedral symmetry or tetrahedral symmetry, they have more degeneracy as compared to a non-unsymmetric system. Again, I hope Aninda is going to discuss more on this. Now let us look at the wave functions. Okay, if you look at the wave functions, you will see that for a 2D wave function, it's basically going to be something like this, which is shown on the top left, right? And if you look at this particular wave function, it is basically like some sort of a bell, right? It's a square. It's more not a very symmetric bell, but it's more of a bell which is inside a square, right? Or you can think of it in the Dhobi Ghat. If you go to the Dhobi Ghat, if you take a square chadar and two friends of you hold it on the two sides, or the dhobis are doing the same thing and they're trying to dry it, right? Then, or I can do the same thing with a handkerchief, right? I'm going to get one particular wave, right, kind of thing. That is what the wave function looks like. And if you do it the same thing at a higher, faster pace, if you give it more energy, you will see a ripple forming. You're going to basically get, some sort of a wave-like behavior that is going to happen for n equal to nx equals. For the first one is nx equal to 1 and y equal to 1. Second one is for nx equal to 1 and y equal to 2. I'm assuming that this axis here is the ny axis, okay? And the same relationship is maintained, and number of nodes remain as ni minus 1, okay? And with the bottom one here, bottom left one here shows nx equal to 2 and y equal to 2 state, all right? It's very easy to plot, but you remember this relationship. Now, let's do a quick quiz. And let's try to find out what are the values of the nx and ny for these three systems. These are just like your like this egg. You've seen this egg wallas, egg sellers have these baskets where they keep eggs there, right? It is something like that. It's very similar to that, right? That is what the pattern is going to be in terms of what the wave functions are, and the probabilities are just going to be the square of it. So all the negatives will become positive and nothing else. Zeros will still remain zeros, all right? Where the nodes are, they're still going to be there. So all you need to do is figure out how many nodes are there in each of these different states. And from these nodes, you can predict what the quantum numbers are going to be. Once you know what the quantum numbers are, you can predict what the energies of each of these states are. Okay? So I'm not going to give you the answer, but I want you to, number of nodes, remember, is going to be n minus 1. That is applicable for both the x as well as the y dimensions. All right? Okay. Now we move on to a little bit more complex situation. Okay. Go from, did everybody get that? Everybody, I hope everybody got this. Okay, good. I'm getting some good answers. Sachin Sabu Sarkar, lowest is 2, good. Middle one is 4, 1, 2, 3, correct. Upper one is 1, 2, 3, 4, 5, 6, absolutely correct. Ahi, SH, as well as Susim Sabu Sarkar, they have all given the correct answers. Okay, everybody can easily find out. All right, so now let's go back to a little bit more complex situation where we have a vehicle or a quantum particle in a 3-dimensional box. Okay, it's confined in a 3-dimensional system. So just analogous to what we have done earlier, you can now have your wave function, because the Hamiltonian can be separated again in x and y and z, now 3 variables. You can now write your wave function as a product of 3 sine functions. One will be of x, one will be of y, one will be of z. And if you have the cube, instead of a cube, it's a cuboid with the lengths of the cuboid being a, b, and c, then of course I'll have different energies will be represented as essentially some constant. We don't worry about too much. Some beta prime, we decided we'll call it beta prime, times nx square plus y over a square plus ny square over b square plus nz over c square. And here we have three quantum numbers for three dimensions. And these three dimensions, the quantum numbers in three dimensions, each of them can take values of nx, ny, and nz can take values of 1, 2, 3, 4, and so on. So all positive integers. Now, how do these things look like? Of course, I mean, I would appreciate, I think, if you really want to do this better, you need to write down, you need to calculate the energies for these different levels. And I like this problem a lot, where I have given one problem, I think, in the tutorial sheet, which asks you to calculate the energies. But it will be even more fun if you go from a 2D box to a 3D box. And let's just assume that you have n equal to x equal to 1 and 2 and 3 and nothing else, and calculate the energies. And you will see how it's tricky. It's not necessary that everything, it looks very simple, but you can easily make mistakes to get the relative energies right. How do they look like? This is way more difficult to represent, because you have, for humans, we can only perceive three dimensions. So here the fourth dimension has to be the value of the wave function. So I can't really plot it. So these are contours of these wave functions at given values. You can see that. So it's very difficult to perceive, or visualize this. But the only one which can be visualized very easily is the wave function for psi 1, 1, 1. Okay, that is nx equal to 1, ny equal to 1, and nz equal to 1. That does not have any nodes. As you can see, number of nodes is the quantum number minus 1. So that doesn't have any nodes. So it's essentially like looking at the sun from outer space. Okay, so the center will have the maximum intensity, and as you go outwards, the value of the wave function is going to slowly go away. And in any direction that you go to, essentially it will follow x or y or z. It will follow some sort of a sine curve. Okay, so that is how it's going to follow from the center of, actually not sine curve, more of a cos curve from the center. Okay, so that is how it's going to look like from the center. That is how it's going to look like. All right. Okay. So then I'm going to take a very quick set of questions, and then I'm going to go into any other applications that I have in mind that I'm going to discuss. That's more realistic. A lot of people I know are waiting for applications, so I'm going to talk about the applications. But if you have any questions, please say so now in the chat box. This is not very complicated. What we have talked about in the last small session is actually not that complicated. Okay, I'll wait for you guys to ask more questions. Think and ask if you have questions related to particle in a box. Did I miss any questions before? Do we have any questions? Okay, we have a question from Prahlad Shana here. Shape of 211 in 3D looks like a p orbital. Okay, this is, you're talking about, Shana is talking about 211. Yes, it is actually, no, there's no relationship between the p orbital and this one. Prahlad Shana has asked this question, but well, I don't really know whether it looks like a p orbital or not. It's actually just two oblate spheroids. Okay, that's it. So there's no relationship between p orbitals. I have a question from Sugata Chakraborty here. Is there any analogy between square planar geometry complexes and square box model? No, there is no analogy as such between a square planar geometry complex and a square box model. To my understanding, there is none. Uh, Sagar Kadam has asked a question: when we calculate psi function, uh, do we consider the time variable? No, we don't. We have already gotten, Sagar, we have already gotten rid of time much earlier. Okay, the moment we separated time out from the time dependent Schrodinger equation, we separated out and we said that we will not bother about that anymore. We are only going to bother about the time independent Schrodinger equation. So we do not consider the time as variable anymore. We have a question from Susim Sabut Sarkar. I can't get the difference between vibrational and rotational system. Can we just discuss it? I don't really want to discuss it right now, Susim, because this is not related. But in a vibrational system, is where the situation is like this, where two atoms are vibrating. It's just like a simple harmonic motion. So you can think of relative to one atom, another atom is vibrating like this. Okay, and you can model it using a simple harmonic. You know what the Hooke's law is, and you can do the quantum mechanics, and you can put what the potential energy is going to be, and the kinetic energy operator is going to be, and you can solve it, and you get certain wave functions and certain energies. And in the rotational case, it's basically like a rigid rotor. So it's like a pen where this distance is fixed and it's rotating in 3 dimensions. It's not 1 dimension, but in 3 dimensions. And so that rotor, you can also write the Hamiltonian for the rotor, and you can solve for the wave functions and the energies, and you get certain energies, and that is how it is. So you just have to open up books, or you can open up YouTube, or you can open up Wiki, and you will find the answers. It's not really that complicated, okay, these two situations. Then we have a question from Sanjay Lala. Particle in 1D, 2D, and 3D box are having any practical application? Yes, we are going to talk about that exactly in the next half an hour. Less than that, perhaps 20 minutes. So it should be done. Can this theory be used specifically? Fox Steep is asking, can this theory be used in special theory of relativity? I have, again, no idea. I have no idea, Mr. Fox Steep, because special theory of relativity is something that I don't understand at all. And so, again, my apologies for my limited knowledge, and I won't be able to answer this question, how this theory can be used in special theory of relativity. Okay, thank you. Thank you for the clear answer. All right, done. All right, let's move on. I think people have been waiting a lot for applications, so let's talk a little bit about applications. Well, the first application in chemistry is something that many of you are already familiar with, and that is the idea of having conjugated systems or conjugated molecules, or understanding the electronic spectra of conjugated molecules. Now, you can take molecules such as beta carotene, which is a part which is there in your eyes, which is also present. Similar molecules are present in photosynthetic systems, and a similar molecule, this is present in carrot, is all trans retinal. You have these alternate single bonds and double bonds, and when you have alternate single bonds and double bonds, essentially you know that this is a pi conjugated system, and if you have this electron, these electrons can freely, or at least one electron can freely move around this length. This electron cannot just escape out, so it's like of the system. So you can imagine that the electron is confined from this end here to this end here, right? So this situation and this direction, effectively the electron can't move in this direction much, because this direction is almost not much to move, right? So the free movement is happening essentially along this long axis. So you can model this as a one-dimensional system, and if you do that, you can do the spectroscopy of a particle in a box, 1D box, right? And if you do that, again, I mean, the idea of modeling this is a very, very simplistic model. I mean, this is probably not necessarily true that everything will work, but the idea is that there's going to be at least one electron, one particle, which is kind of free to move from one end of the box to the other, because the moment one electron is moving to one end of the box, you're generating a plus charge on the other end of the box. So essentially, you are this inside the potential is no longer zero for the second particle. Okay, so it's only one particle which is moving around. And once you know how to do the spectroscopy, because you can start doing some predictions. And the question is, does the particle in a box serve as a good model or a bad model for the system? And if you do the measurements, and you may find out some answers, and sometimes answers are going to be good for certain molecules, sometimes answers are not going to be so good for certain other molecules. Now, does this make the model a good model, the particle in a box model, a good model or a bad model, is really what I want to discuss. And I wanted to ask, tell you at least that, what is it that makes a model good model, and what is it that makes a model a bad model? Now, if you look at the expression that is shown here at the bottom, you will see that the energy, or h nu, the light that is absorbed, or the photon energy, is essentially inversely related to the square of L, or the length of the box, right? So that means this particular model of particle in a box has this predictive nature that tells you that if I increase the length of the box, then what's going to happen? I'll have a decrease in the energy between the consecutive energy levels. So if you think of the HOMO and the LUMO of the molecules, highest occupied molecular orbital and the lowest occupied molecular orbital being separated by some energy gap, which we are going to monitor. So you can imagine that those two levels are going to come down if my length of the box increases. If it becomes shorter and shorter and shorter, the energy gap becomes more. The amount of wavelength that is going to be absorbed or emitted is going to be a shorter wavelength, higher energy, and for a longer conjugation length. And that's really the nice predictive nature, which tells you that if you take a series of molecules, which are shown over here, okay, particle in a box, although it may not give you very precise answers for the wavelengths of absorption as well as emission for any of the molecules. Sometimes they do give good results, sometimes it gives bad results, okay? Way off. But what it does do correctly is predict the trend correctly, okay? Now, when I mean by predicting the trend, essentially what I'm saying is that even as an undergraduate student, by looking at the molecules, you can see clearly that the molecule at the top has the lowest conjugation, which will absorb the lowest energy or the lowest wavelength of the highest energies. And the particle at the bottom here, which is the highest conjugation length, will absorb the lowest energy and the highest wavelength of light. It will absorb in the red, and the one in the middle will absorb somewhere in the middle. Okay, this predictive nature, which we cannot tell offhand, by just looking at the molecule, what the relative absorption wavelengths are going to be, or the emission are going to be for these two molecules. But this comes straight away if you have seen what the energy expression for a particle in a box is. And we use this idea to explain spectroscopic systems, or spectroscopy of many systems, where we talk about conjugation length being more, and therefore the energy is absorbed is less. And so the wavelength of light that is going to be absorbed or emitted is going to be at higher wavelength, and vice versa. Okay, so this is the first real application in chemistry that we are, as an undergraduate level, we can understand that. The second one that I'm going to talk about is an application of the particle in a 2D box. Okay, now in 2010. A very young guy, he was almost my age now. He got the Nobel Prize. His name is Konstantin Novoselov. Okay, and this is the picture of this guy. and that is the age at 36. He or 34 or 35. He was a postdoc. He got the Nobel Prize. One of the youngest postdocs in physics or persons in physics to get a Nobel Prize in recent years, and he got this Nobel Prize for the discovery or work on graphene, how to make graphene. Graphene is this molecule. Many of you have heard of it as a very, very important molecule for molecular electronics. And graphene is essentially a single sheet of graphite. Okay, so if you take graphite, which is layered of sp2 carbons, and if you peel off one layer, okay, what you're going to put it on a surface or not, what you're going to get is graphene. Okay, and there are very, very special properties of graphene, many special properties of graphene, but I don't want to talk about that. But what is interesting is that in a graphene, you would imagine that graphene is a system where electron can freely move around, because in the pi clouds, they are kind of, all the pi orbitals are kind of up and down below, and they can move around over extreme. So the delocalization length of electrons in graphene is expected to be really, really large. Okay. But spectroscopically, when you do spectroscopy, people found out that graphene absorbs and emits light at a reasonable, in the IR, in the infrared region, which is far, higher than in energy than what you would have expected if the electrons are free to move over very, very large distance. And using the same formula as we had done in the previous slides here, people were able to kind of backtrack and obtain the effective delocalization length of graphene, and which kind of tells you that graphene is not really this super flat sheet that you would imagine, but it's actually more of, it's more of a rolling sheet, like the rolling planes and that you see in pictures of rolling planes in Europe. Or even here in Maharashtra, you can see such rolling planes if you go to Nashik areas, Nashik or Pune. So it's some sort of a conjugation lengths are being restricted to reasonable lengths, which is in the order of a few tens of nanometers, and not more than that. And that is something that came off as a direct application of the usage of the theory of a particle in a 2D box in real life. And graphene, as I told you, have a lot of real life applications in terms of making molecular electronic devices. The third example that I'm going to give you is the idea of this. Somebody asked me quite some time back, can we talk a little bit about your research? And so I'm going to come to a little bit of my research. The idea of nanoscience. The entire nanoscience builds up on this idea of this quantum confinement concept. Okay? Quantum confinement in the sense that something is getting confined in a semiconductor material. And the people don't really understand, most of the undergraduates don't understand what the confinement is about, what is confined. And so let me first describe to you what is confined, and then we'll try to understand. Okay. Now, in a semiconductor material, as shown over here, if you shine light, what will happen is that you will take up an electron from the valence band to a conduction band. Why? Because in a semiconductor material, the valence band and the conduction band, they are separated by some reasonable amount of energy. And using shining light, you can generate electron and a hole pair, where the electron gets excited to, or gets into the conduction band, and a hole is retained in the valence band. Now, physically, in the energy scale, yes, the electron and the hole are getting separated, but physically, the electron and the hole are actually very close to each other. Okay? And this one is plus charge and one is a minus charge. So they are attracted to each other, and they are moving. The electron is moving around the hole, just like almost like a hydrogen atom, but without any mass of the hydrogen atom. Okay, it's a mass of the hole, which is very different from that of a hydrogen atom, or without the mass of the proton. So that is what is pictorially depicted here on the top right. And these are these excitons. These are called excitons, and they are Excitons because called excitons, I presume, because you need to excite the system with light to generate them. So they are actually not real particles. They are quasi-particles. And the idea is that these quasi-particles, they can be formed using light. And then there's electron in the hole, they can recombine, and then light can come out of it. Okay. So once light comes out of it, then they disappear. They just vanish. And so these are called quasi-particles. And essentially, when I say particle, what I really mean is not particle, but wave vehicle, right? So they are also quantum mechanical in nature, and they are quasi-wave vehicles, and they are present in the crystal. So when they're present in the crystal, they can continuously be generated and continuously be annihilated. So a light gets absorbed and light gets emitted, right? That's the process that happens in a bulk crystal. Now, when you take a bulk crystal and start chopping it, and make a nanocrystal like a small ball of crystal as shown here on the lower left, essentially very funny things can happen. And these are realistic because you can actually image using transmission electron microscopy, which again uses an application of particle in a box in some sense. It's a leakage through a potential barrier. That's an application, that is an extension of particle in a box in some sense. So this transmission electron microscopy allows you to visualize using the contrast of the electron transmission through this crystal, the presence of these nanocrystals. Okay? These are an array of nanocrystals, almost forming a lattice, as you can see, and their sizes are in the order of 5 nanometers. All right, and these quasi-particles are much smaller. They are in the order of nanometers or even less than nanometers. These excitons. So if you confine these excitons in this small region, which is this ball, very small ball, let's say in the order of 10 nanometers or so, then what you will achieve is a particle in a sphere. Okay, it's not particle in a cube, but particle in a sphere. Now, if you have particle in a sphere, what is going to happen to the energy level? The more you confine, the smaller you make the sphere, the energy levels are going to get separated. The larger you have the sphere, the more closer these band gap or the conduction and the valence band are going to come closer to each other. So effectively, you can separate the conduction band and the valence band energies. Now, I'm not really saying exactly the right things here because we haven't done the hydrogen atom, and I don't want to go into more details. I'm not saying exactly the right thing, but I'm saying roughly the right thing. But effectively, for the same material, it's very unlike molecule. Molecule, you have the same molecule, it will have a certain characteristic wavelength of absorption. You have different materials, there are different colors of light are absorbed or emitted. But here is the same material, same semiconductor material. Let's say it's a cadmium selenide or cadmium sulfide. You make this nano confinement or this nanocrystal smaller and smaller. You have a larger energy gap, so you will have a lower wavelength or higher energy of light will be absorbed and emitted. On the other hand, if you make this ball bigger, instead of this small ball, you make a bigger ball, then you are going to have this energy gap coming closer to each other. So you will have a lower energy or a higher wavelength of light will be absorbed and emitted. Okay, this is the idea of quantum confinement, and which is applicable in nanoscience. Now, how do I really use it? Now, the concept that I just told you, confinement of excitons, right? Now, this is exemplified here. This is a guy, Louis Bruce in Columbia, and then Mounji Bawandi in MIT. They were the pioneers to do this. To show that you can essentially create these balls in nanoscale, ranging from, let's say, 2-3 nanometers to 20 nanometers in size, where you can essentially tune the color of the light absorbed and emitted in the entire visible range, okay, from 400 nanometers to 800 nanometers. Even higher and even lower wavelengths can be achieved by doing this thing. And these quantum dots, they're called quantum dots because they are almost like individual molecules, all right? And the reason they're called dots, because this confinement is happening in all directions. That means this exciton is confined in 3 dimensions. So it's almost like formation of a dot, or a particle, which is there. And they are very, very bright. They are super bright. Okay, they can generate a large number of excitons, and the excitons can emit very efficiently, because the electron and hole, they are confined in a very small region, so they can recombine very efficiently, and they can emit light very efficiently. And they have tremendous applications in chemistry, biology, and material science for photo emission imaging purposes. All right. And these guys are so bright that this is where kind of my work comes in. They are so bright that you can actually detect the emission that comes out of one quantum dot. So you can physically separate them. There are techniques to do that. This is an image which shows you the image of a single emitter or a single quantum dot in space. Okay, this is each of them, each of the spots that you see here, they are actually coming from one quantum dot. And the experiment that I do is actually related to this. I do measurements on single particle imaging or single quantum dot imaging, and I do spectroscopy and spectroscopy essentially means finding out what color of light, what is the purity of the color of light that is emerging out of this individual nanocrystals. And here, this particular experiment that I did here, I mixed a whole bunch of quantum dots of different sizes. Some of them were larger, some of them were smaller, some of them were intermediate size. And you can predict, of course, you can predict which are larger and which are smaller if you have a color image of it. And in fact, each of these spots, they originate from one quantum dot and one quantum dot only. And there are ways to figure out how that is so or why that is so. But they are so bright that you can even visualize the colors using your unaided eye. That means using naked eye. If you look through the microscope object in eyepiece, just like looking through a telescope, and these are almost looking like stars, isn't it? Then you will see that you can see they have different colors of light that are emitted. You can see many of them are yellow, and some of them are red, some of them are green. And so without looking at the size, because the size is not a good reflection, because these are diffraction limited spots, which is limited by the diffraction of light. So they'll all look at the same size, but the color, the green color tells you these are particles which are of relatively higher energy, lower wavelength. The red ones are the ones which are of lower energy, high wavelength. So they must be the bigger particles. Green one must be the smallest particles. And the yellow ones and the orange ones are the ones which are of the intermediate size particles. But looking at the colors and doing spectroscopy of individual particles and looking at the colors of the individual particles, you can tell which ones are of which size, or at least relative sizes can be predicted. Now, I don't want to go too much into the details of my work here. I just wanted to flash only one slide and tell you that this is what my research is about, to understand the differences in the spectroscopic behaviors and the optoelectronic behaviors of individual nanocrystals and quantum dots of various kinds. That's really what I work on. But these nanocrystals, these super bright and pure in color, you can see the color purity here. Some reds are very pure reds, some green are very pure greens. This has led to a lot of different applications. Okay, one application is in quantum dot based solar cells, where you can use this high energy, high band gap, the smaller size quantum dots can be used to absorb UV light, which can now transfer the energy to a little bit larger quantum dots, which have smaller energy gaps, which can even convert it and transfer the energy to even larger quantum dots, as you can see here in this cascade thing that I've shown here, while the larger quantum dots anyway absorbed in the visible. And you can essentially harvest solar energy and convert the solar energy to electricity. Okay, so that is one way quantum dot based solar cells work. The other one is in the applications for biology. Quantum dots are often very commonly used now to detect to do in vivo imaging, not only in cells that is shown here on the right, but also for imaging tumor and cancer in live mouse. Right, you can see here red and green and yellow. They are for different quantum dots, which are connected to. You can combine it, these quantum dots, with antibodies, and they can go in and detect certain things and go to specific parts of your body and light it up and show you and tell you, okay, this is where the tumor is, and this is where where you have to do the operation or remove it, and so on and so forth. Okay, so that is another practical aspect of application of this quantum. And finally, I'd just like to mention, because this nowadays this is also kind of what I have worked on a little bit about 7-8 years back, is the idea of the solid state lighting. All of you have seen these LED lamps in many of your classrooms, or LEDs are there in the street lights, and these LEDs are actually made out of a solid state material. They're solid state LEDs. They're very, very bright, and they are formed due to this alternate layer of this high band gap, low band gap, high band gap, low band gap material. Okay, and this is typically a gallium nitride and indium gallium nitride alternating layers of high band gap, low band gap materials, and these essentially form a 2D structure. Okay, where the electrons and these holes, or these excitons, you can think of it as excitons, these electron hole pairs, they get confined in 2 dimensions, in 1 dimension. That means in the Z direction they get confined, and they are free to move in the plane, as you can see here. Okay? And due to this confinement, there can be very efficient recombination of these excitons, and that can lead to very, very high efficiency of emission. And they are inorganic solid state materials, so extremely stable. So there's no photo degradation of the material. They're very, very stable, and they are very, very commonly used as lighting, and a lot of energy is being saved by the introduction of this lighting, the solid state LEDs. And as you can see here, this picture here at the lower bottom here kind of shows you, the hole and the electron coming in and recombining and emitting the emission of the photon. And this is extremely important, relevant to society, because a lot of energy is being saved, and this is again a direct application of the particles in confined in a 2D box model. Okay? This is like electrons and holes are these particles which are confined in a 2-dimensional 2D system. The third direction it cannot really move. Okay, so that is the idea. So what I'm going to do is I'm going to stop here right now, and I am going to discuss, take some of the questions and doubts. But before I do that, I'd like to just mention one more thing, and that is, I'd like to tell you that there is a prescription. Well, let's forget it. Let's not go into hydrogen atom any today. Today I thought that maybe I'll very briefly tell you a little bit on the hydrogen atom, but perhaps today is not a good day to do that. We have already covered a lot of stuff. People are tired. We have spent more than 2 hours already. So let me take some questions, and then we can decide what to do from there. Okay.
Dr. Arindam, could you take the questions from the YouTube, because Khalida is having some issues with her network?
Sure. I am actually taking the questions from YouTube. Let me see what people have already.
There are no questions on Teams. There are no questions.
Okay, good. So let me see what kind of questions have been posed already, and then I'll be able to, Okay. Particles in a 2D box. Okay, question. Sanjay Lalla. Practical applications. So Sanjay, I hope I have answered your question of applications of particle in a 1D, 2D, and 3D box. Okay. Well, I didn't really talk 3D box, but it was more of a sphere. It's a 3D system. Then I have a question from, is there a correlation between box normalization and boundness of energy? No, there is no correlation between box normalization and boundness. I don't understand what is a box normalization. Question by Rohan Mitra, but I do not understand what is the meaning of box normalization. Normalization is happening for the wave function. Okay, And boundness of energy is some also I don't understand boundedness of energy what it means, but so Rohan Mitra, I actually don't understand your question. Please rephrase. Um, any zero dimension particle application? We talked about that. Talked quantum dots. Um, this is a question by Sivagiri. Then there's a question by Sagar Kadam. Uh, while we're discussing vehicle here, does this vehicle stationary or traveling? Now, again, when we are talking about quantum particle, we should not be asking these questions. Okay, Sagar Kadam has asked this question, but we don't really care. We give a damn about whether the vehicle is stationary or traveling because this is a quantum particle. We cannot talk about its path. We do not really know what it is doing. Only when we are doing a measurement we know. But it may be traveling, maybe it's stationary. God knows. Okay, so that's the answer to you. Sudeepa Aich is again asking a question. Is the degeneracy arises for 2D box having Lx not equal to L by? Yes, of course, you can indeed have degeneracy in a 2D box, particle vehicle in a 2D box in Lx is not equal to L by. And those are called accidental degeneracies. Okay, that is happening because that's going to happen because of the relative lengths of the boxes. Okay, so if you happen to have Lx is twice Ly or Lx is 4 times of Ly, then you will see that if you do the calculation, you will find out that for certain values you are going to get some degeneracy. So that's absolutely possible. No problem with that. Then we have a question from Juhi Pandey. How can we calculate the degeneracy particles in a ring? It was asked in GATE 2017. I am not sure how to answer this question now because to do for particles in a ring, I have to solve the particles in a ring. And if you solve particles in a ring, you will find out that there will be degeneracy that is going to come in. I have to think about this and answer this question. Okay, I have to solve it and answer this question. So, and since we didn't talk about much about particles in a ring, I'm going to hold on to this. I'll try to get back to you separately if you email me. What if the molecules? There's a question by Siddhi Gaurav. What if the molecules have the same amount of conjugation? Then how can be analyzed using particles in a box? Well, I mean, if molecules have the same amount of conjugation, then conjugation length, then they will a particle in a box would predict that they will have similar energy. But in reality, so you won't be able to discriminate between two molecules with similar conjugation length using the model. But there'll probably have some other education. Then how can we analyze using particle in a box? Well, I mean, if molecules have the same amount of conjugation, then conjugation length, then they will a particle in a box will predict that they will have similar energy. But I think there is a madam, you have to mute. Discriminate between two molecules with similar conjugation length using the model. But there'll probably have some other education. Then how can we analyze using model? Madam, you have to mute. There is an echo coming. So the question, the point is that you will not be able to because if the two conjugation lengths are the same, that's the same prediction that is going to have particle in a box model will give me the same prediction. So the point is not that really. The point is that if you have molecules of different conjugation length, particle in a box does a pretty good prediction in terms of predicting the relative energies of these three or two or this series of molecules which have different conjugation length. Then there's a question by Susim Sabut Sarkar again, but sir, IR is electromagnetic radiation. That means that potential depends on Vxt. How does this experiment of 1D box get success? Okay, I think Susim, you are getting a little confused here. Yes, radiation is going to be potential, will be a function of time. But when you are describing a system, there is, when you are defining the energies of the system, that you're considering time independent of Schrodinger equation, right? So that has nothing to do with the absorption of radiation. Absorption of radiation involves uh, considering time dependent Schrodinger equation and solving for it and getting the transition. In fact, an oscillating electric field with space and time, which is basically where the V is a function of x and time, that is going to induce the transition. Okay, so that is not contradictory uh, to what we did. We did the evaluation of the energies using time independent Schrodinger equation, and we got the energies of the system. Right now, what you're saying is that electromagnetic radiation comes in and interacts, and that does a completely different thing. It induces an absorption, and for that you have that happens because B is a function of x and t. Okay, so it is not contradictory. All right, then we have no other questions. I guess there's no other questions so far, unless I have. I have this button here. Good, good, good. There are a few more questions, I think. This is all like good afternoon. Beautiful applications. Okay, Sanjay Lalla. Then thank you for valuable information. Excellent presentation. Okay. Thank you. Valuable time. Good afternoon. Good informative session. Okay. Please feedback. All right. Next sessions are 2:30. Okay. Okay. Previous questions itself. Okay. He SH is, and in the previous question itself, however, the holes in electrons are separated into two layers. Yes, I guess he is asking me a question on the very last slide that I showed you, that the electrons and holes are, yes. And that is because here the electrons and holes are not being generated using photons, all right? In this application that I mentioned at the very end, in this application, the electrons and holes are actually being generated by electric field. Okay, so you're generating electrons artificially, and then in a solid state lighting device, it is the opposite of a photovoltaic device. Here you are applying an electric bias in a field and generating light. Okay, so that's why the electrons and holes, if you look carefully, they are present in separate, but they can come together and get recombined in this very thin layer where there is a confinement is in one dimension. It's a 2D system. Okay. Then there is a question by, okay, no, there is no, thanks, sir. Electric field, yes. I think Yashashini Gupta has already answered the same question that I just said, is the electric field. Maybe Ahish. Ahish, actually, not Ahish, it's Ahish. Sorry about that, Ahish. Okay, I think that's pretty much what I got now, unless there's any other question. I don't see any other questions coming, so it's already 1:33. So unless you guys have any other questions, I can wrap up. I wanted to share one small thing. It will take 1 minute, and I will include that slide and keep it with you in the in the Dropbox. Is something that is useful, I feel, for students, and that is a flow chart. So, and I teach that when I teach hydrogen atom, and what we learn from what is one flow chart is very, very useful for you, and I hope this will also be useful for you. But I guess the last part will not come. Well, I'll move it up and help you with that. So I want undergraduate students as well as master students who are learning quantum mechanics to kind of remember this flowchart. If you can hear me. So this is what we really did and what we learned from particle in a box is that, first of all, you have to formulate the Hamiltonian. Okay. Now, a lot of people have the confusion that a Hamiltonian is same for all systems. It's not true. As we have already seen, different systems will have different Hamiltonians. So you have to construct the Hamiltonian correctly, get the potential energy right, the kinetic energy terms right, and you have to construct the differential operator, differential equation correctly, which is nothing but the Schrodinger equation, the time-independent Schrodinger equation. And then you have to use separation of variables and use intelligent or trial guesses. After you achieve this, once you get to the solutions, the next step that you have to do is impose boundary conditions. This is how you solve a problem using quantum mechanics, all right? Now, once you impose the boundary conditions on the eigenfunctions that you've gotten, you automatically get the quantum numbers. Eigenfunctions, and we need to ensure that they are well behaved. So that means we also have to normalize the wave functions. Once we get the normalized wave functions, now from this information, you can get the energies of the states corresponding to the quantum numbers and also the quantum numbers, right? Once you have all these things, then you have the total wave function available to you. Then you know how to do calculate the average values and the probability, all right? Now, this prescription, if you have this prescription with you, then if you have this prescription available to you, then you will not have any issues in figuring out or solve other problems. And the same is kind of true for how to solve a hydrogen atom, for instance. You will, when you do that to get the wave functions of hydrogen atom, you basically have to follow the same procedure, right? It's a little bit more elaborate, a little bit more complicated, but philosophically it is not complicated. Mathematically it's complicated, but philosophically it's not complicated, all right? And eventually you can get the probabilities and average values by using the prescriptions that quantum mechanics provides. Okay. All right. So I'm going to end here, and I hope there are no more questions. I deliberately gave a little bit of time here. Okay. I do have, I think, one question or two questions here. Let's see. Let's see what I have here. Okay, Rohan Mitra wants to repeat. I will repeat the question that for particles in a box problem, you can conclude both normalization and boundedness of energy, but for free particle, we can't do this. Can we conclude from this aspect? Can we conclude from this aspect? We can conclude both normalization. Yes, for a free particle, you can't even normalize the wave function. That is correct. In fact, that becomes a real problem because we cannot normalize the wave function. And once for a particle confined in a well, you can do the normalization as well as get the discretization of energy or quantization of energy. The boundedness is not really a correct term. Okay, then thank you. Okay, then I have a question from Prahlad Shai. Sir, how is Hamiltonian found in complex molecules? How do computational chemists do it? See, I mean, it is relatively simple, actually. If complex molecules means you just have to find out for each particle, you will have a kinetic energy term. For each particle in a system, you'll have a kinetic energy term. And you have the potential energy term will be from the interactions of each of those particles, you'll get several potential energy terms. So for each pair of particles, you are going to get a potential energy term. So you have to find out, you can read up any book on this, you can look at the hydrogen atom or hydrogen molecule, how to get the Hamiltonian, and the complexity just goes more and more as we increase the number of particles in a system. But essentially, you have to calculate find out the kinetic energy term, you have to find out the potential energy terms. And then you do some math and simplify your Hamiltonian to something manageable, and then work on it and do the computation that you need to do using quantum chemistry. Okay, please send feedback link. Okay, and thank you. And guys, everyone who's still hearing me and who are still there, please provide feedback. I'd really like to appreciate anything that you felt didn't go well or some problems. If you can tell me what the problems were, if you didn't understand anything, you felt something difficult or some unusual problems, please be critical. Let me know what you didn't like. I'd like to take your feedback to improve upon myself in the future. Okay, can you talk once on confinement? Well, Ankush Sharma has asked me to talk about confinement, but uh, as I told you already, we discussed about confinement at length today, the entire day. So it will be very difficult for me to talk about confinement very, very briefly. Okay. So maybe next time I can do that. But again, as I told you, you need to go up back and look into YouTube videos. I mean, you can learn so much nowadays from just going to YouTube videos and search for quantum confinement in YouTube and see what they say. And rather than you'll probably get a better solution there if you want to learn a little bit more on a subject. All right. Okay. I guess. Wonderful. Okay. Thank you. Okay. Thank you. Thank you for listening, everyone. Thanks for listening. Relate symmetry and quantum mechanics or orbital grasping. Okay. Anand is going to talk about that. This is by Shushrut Shubham. So could you take another lecture covering hydrogen atoms sometime later? Sure, I'd be glad to you to talk to Madam, Lakshmi Madam and your teachers and RSC to arrange a couple of more lectures. I can cover hydrogen atom in two 2-hour sessions if you'd like. I'd be glad to do that. Explain all your questions of hydrogen atom once more. Please, Yashashwini Gupta, okay. Please convey to your teachers about that and RSC. I'll be glad to do that. Information sharing, a lot of studies. Nice. Thank you. All right. I guess that's pretty much it. So I'm going to stop the session. Thanks again a lot. Thanks a lot for being there and listening. And hopefully I have been able to get you guys enthused a little bit. And hopefully you will start reading up books. Not only watch videos, but just read up books and try to figure things by yourself. I think what I told you today and yesterday is enough for you to get yourself, motivated, and you should be. It should be enough for you to understand what the books are trying to say. Okay.
Okay,
So Lakshmi Madam,
yeah, just a minute, sir. Just a minute. Yeah, thank you, Dr. Arindam Chaudhary, for the excellent sessions 2 days. And we are really sorry that yesterday there were some technical problems.
No, that's I understand it's my fault. I didn't know that. Also that none
okay.
of us knew that a Mac will create a problem like this. So
And we really look forward to more sessions because from the interactions that students have raised questions, I think it has really motivated them and set them thinking on several aspects of quantum. So I really look forward, and we'll try to see if we can arrange some more sessions with the help of RS.
I'll be glad to take cover on, let's say, hydrogen atom. I'll probably need 2-hour sessions, but
I will try to work it out. And thank you very much.
We can do that after a month or so or whatever. Yeah. If we can rope in RSC, I think that will be good because then it becomes a nice way of doing it. Officially.
And thank you very much, sir, for your time.
No, it was a pleasure. It was a pleasure. And it was a great interacting with the students. There was amazing questions, actually, most of them.
Students this time, because it is an online, we are having students from all over India. I mean, practically, it's representing every state. So it's a different.
I didn't know that. They're
not only confined to Mumbai, but it is from all over India. And we are happy. And participants, thank you for being there. The next session will be starting at 2:30 by Professor Ananya Datta. And I think what symmetry and quantum relation, which you were raising questions, I think Dr. Professor Ananya Datta would be referring to that. He mentioned it yesterday also in his lecture that he would be taking it up from there after your session today. Thank you very much, Dr. Arindam.
Thank you so much. I'm going to sign off now.
Yeah. Thank you.
Okay.
Bye.
Thank you for inviting. Bye. Bye-bye.
Hello, hello, hello.
हेलो अंजना.
बोल लक्ष्मी. हाँ.
Don't talk. It is YouTube में है.
अच्छा, okay, I'll not talk now. Okay, okay, okay.
Hello.
Yeah, hello, sir. Good afternoon.
Good afternoon. I think I clicked the wrong link by mistake and went to yesterday's meeting.
Okay. Today the link has changed.
Yes, so now it is fine.
I'll just
I
see
am
how
in
many are
the
logged in.
correct YouTube link definitely,
Okay.
because there people were asking questions a little while ago as well. So
Okay.
I think we are all set.
And let me see if it is. Yeah, there are 41 students. I think we can start, no, sir?
Yes.
Because
I'm
they'll
ready.
join in. I mean, people do join in.
Yeah, sure. We can begin.
Yeah. Okay, good afternoon, everybody. And it's my pleasure to welcome Dr. Ananya Datta again for the second session. And yesterday he discussed about the basics of symmetry in chemistry. And I think today sir is going to discuss, because Dr. Anindam Chaudhary mentioned that you would be covering symmetry and quantum. So I suppose you might touch upon that also. And also the matrices. So welcome, sir, once again, and look forward to a lot of learning.
Thank you, ma'am. I'll begin. Let me just share my slides.
Yeah.
Can you see the slide, and is it full screen?
Hello, I can see the slide on Teams, but I'm not on YouTube. So could you check in YouTube if it is seen?
No, in YouTube it is not come yet. Usually there's a lag.
Time lag.
Yeah. So we'll just wait for it to just show up there, and then we'll begin.
Yeah.
So YouTube is on, but there you can only see this background of yours.
College?
Yes.
Okay,
Yeah,
I'll just check up with. I'll just check.
People are coming in one by one. Now we have 58.
Yeah, I'll just check up with.
Okay.
Now it is seen on YouTube. I could see it.
Yes. All right. I think we are now ready. Well,
yeah, I think
now they are seeing the slide that I had earlier. Now we are all set. We are. Now I'm going to begin. Good afternoon, everybody. We'll continue with the discussion that we started yesterday, but today we'll have a little different flavor than what we had yesterday. So before anything else, let me put the cart before the horse. Because there have been many questions about what is the relationship between quantum chemistry and symmetry. So let me just start with that, even though ideally this discussion should have come later. So let me pick up quite a few notches after where Arindam has finished today. Let me talk about molecular orbital theory of polyatomic molecules in a very, very qualitative manner. So I'm going to discuss the delocalized molecular orbital theory picture of methane. And this discussion is completely from the Symmetry book by Carter. I don't remember the name. I think Symmetry in Chemistry or something like that. The author is Carter. Whoever is interested in learning this more is referred to that book. Of course, other books also have discussed this. Now, we are familiar with molecular orbital theory, I presume, because nowadays, even in class 11 and 12, they talk a little bit about molecular orbitals. An orbital, just so that we are on the same page, all of us, an orbital is a one electron wave function. If this wave function is of an atom, then we call it an atomic orbital. If this wave function is associated with a molecule, then we call it a molecular orbital. But let us be very, very clear that that orbital is a one electron wave function, nothing more, nothing less. Orbital is not a region of space in which finding the probability of an electron is maximum. That is the most popular and completely incorrect concept that unfortunately many of us have throughout our lives. So let's get that clear first. Now, how do you get an orbital? You get an orbital ideally by solving Schrodinger equation, wave function, right? The problem is Schrodinger equation cannot be solved for anything other than a one electron system. For hydrogen atom, you can solve it. Or even if you think of something else, something like rigid rotor or harmonic oscillator or particle in a box has been discussed by Arindam. For these things, we can find exact solutions of Schrodinger equation. But introduce a slightest level of complication. Introduce a second electron in hydrogen atom. Then the Schrodinger equation becomes no longer solvable exactly. So what are we going to do? Will we give up? No. What we try to do is we try to use approximation methods and we try to construct the wave function. There are many approximation methods in quantum chemistry, quantum mechanics. So today we are going to restrict ourselves to start with something once again that everybody knows. Linear combination of atomic orbitals to build molecular orbitals, and we are going to talk about methane here. Now, when we construct these molecular orbitals, and to do that, when we take these linear combinations, this is where symmetry comes into play and goes hand in hand with quantum mechanics. We have to remember that atomic orbitals with proper symmetry can only be combined. And in the next 20 minutes or so, this is what we are going to discuss with reference to methane. So for methane, what do we have? First of all, it's a tetrahedral molecule, and it's convenient to discuss this using symmetry. There is a central atom, carbon, and you have 4 hydrogen atoms, all of which are bonded individually to carbon atom. So they are called pendant atoms. Pendant means something that hangs. So you can think that these hydrogen atoms are hanging from the carbon atom. So to construct the molecular orbital, we have to take combination of the central carbon atom orbitals and the pendant atom orbitals. First approximation that we use is that we use only valence shell orbitals. So for central carbon atom, the orbitals that we need to consider are 2s orbital and 2p orbital. All right. So are you all okay with this? If you have questions, as usual, please write in your in the chat box of YouTube. There is considerable delay between YouTube and in between Teams and YouTube, but we'll handle it. We have sort of got used to it from yesterday. No slide is seen, but I can see it on YouTube as well. Okay, so central carbon atom, 2s and 2p orbitals. For central carbon atom, we are not going to consider the 1s orbital at all because its energy is too less, right? We'll only consider the valence shell. This is a depiction of a 2s orbital. This here is a depiction of 2p orbital. And I hope you have not forgotten the discussion we had yesterday. A good way of drawing a tetrahedron inside a cube is to put dots on alternate vertices. That's what we are going to do. So where do we have the hydrogen atoms? If my memory doesn't fail me, I've drawn it in such a way that we have hydrogen atoms here, and here, and here, and here. So we are going to work with 1s orbitals of hydrogen atom, of course. Okay, now there is a, see, people are saying no video, no slides, but no video is correct actually. I cannot see video on this YouTube, so I don't know how to fix it.
Talk to
Full
my
screen.
technician. I'll just find out, sir.
Okay. All right. Seems to have fixed itself. So we'll go ahead. Great. Yeah. Okay. So now there is a very fundamental difference between the 2s and 2p orbitals, isn't it? And we all know this. 2s orbital has no node, so it's perfectly symmetric. 2s orbital has a node, so the wave function has, say, plus sign on the top and minus sign in the bottom lobe. Okay, what that means, I think you know that very well from the discussion that you have had in the morning sessions over the last couple of days. So now what we need to do is we need to take the hydrogen atom wave functions, but it is not as if we are going to take a linear combination where we'll combine 2s and 2p and 1s of p and q and r and s, everything together. All right. We are going to take linear combinations of hydrogen 1s orbitals that, first of all, well, that in the first case have matching symmetry with the 2s orbital, and in the second case have matching symmetry with the 2p orbital. So these two symmetries are going to be different. Right now we are discussing at a very, very qualitative level. Let us see how far we can get in trying to quantify it. Okay, I think I'm back. Am I there? Can you hear me?
Yes, sir. Any problem?
Yeah, can you see the slide? I cannot see the slides.
Because I am on the Teams, I am not able to see on that YouTube, because if I go there, it gets problematic. Let me check.
No, on YouTube it's fine. I mean, there's a lag, but it's fine.
We are going to take a linear combination with combined 2s.
In Teams, I am able to see the slide.
Okay, on the other one as well, so no problem. Okay, I got it. So we're going to take symmetry adapted linear combinations. We are going to take one symmetry adapted linear combination. Well, sorry, I got a little distracted. So we are going to take linear combinations of hydrogen 1s orbitals to start with, which have matching symmetry with this central atom 2s orbital. And such a combination is called symmetry adapted linear combination. A linear combination with a particular kind of symmetry. So now see, this s orbital is completely symmetric, isn't it? No matter which symmetry operation you apply on the 2s orbital, it is going to remain the same. It will not change sign or anything. So if I want to take linear combination of 1s orbitals of p, q, r and s, that linear combination should also be such that it does not change upon applying any symmetry operation. Is that okay? If there is a question, then please write, because this is something that we need to understand. And the linear combination that has matching symmetry with the 2s orbital is psi 1s of p plus psi 1s of q plus psi 1s of r and psi 1s of s. So if I just add up the wave functions, 1s wave functions of p, q, r and s, then this combination has the same symmetry as the 2s orbital of carbon atom. So this is a symmetry adapted linear combination, or SALC as we call them, which is compatible with the 2s orbital. So now when I try to construct the molecular orbital using 2s orbital, the linear combination I'm going to take is this: some coefficient multiplied by the 2s wave function of carbon plus minus some other coefficient multiplied by this linear combination of all these 1s orbitals of hydrogen atoms, which are connected by all plus signs. And I hope you can see that if I have plus signs here, then what will happen? I will have bonding interaction, right? This has plus sign, this wave function. Sorry. 2s orbital has plus sign. P, Q, R, S, everything has plus sign. So if in the linear combination I have a plus sign in between the two, then I'm going to have bonding interaction. If I take a minus sign, then what happens? 2s, let us say, has plus sign, P has minus, Q has minus, S has minus, R has minus. So you're going to have a node engulfing the central atom, and we are going to have the anti-bonding molecular orbital. Are we clear so far? I think even though there's a lag, I'll stop here and I'll wait for the questions to come because we need to clear this before going further. If there is a question, please ask. Can I please tell about the positions of O? What is the meaning of positions of O? I have not understood this, Tasneem. Tasneem, if you can elaborate upon the question, I have not really followed what you mean. So while we wait for Tasneem to ask her question again, what I'm saying is this: carbon atom, the 2s orbital of carbon atom is shown here. That is at the body center of the cube. P, Q, R, S are the hydrogen atoms, and we are working with their 1s orbitals. They are at alternate edges of the cube, alternate vertices of the cube, not edge, alternate vertices of the cube, right? And we are taking linear combinations of these 1s orbitals. The orbital that is the linear combination that is compatible, or in other words, that has the same symmetry as the 2s orbital of carbon atom is P plus Q plus R plus S. So if you combine the psi 2s orbital with the linear combination of the 1s orbitals by a plus sign, then you get bonding interaction. If you combine a 2s orbital of carbon atom with minus sign before the linear combination of hydrogen 1s orbitals, then we get the anti-bonding orbital. Definition of wave function which you study is incorrect. Can we please elaborate it? Yes. Well, I wouldn't say we study the definition of wave function, not wave function, definition of orbital. The definition of orbital that somehow gets ingrained in some of our systems is an orbital is a region of space in which probability of finding the electron is maximum. What I'm saying is that is an absolutely wrong definition. You can construct that space, that's not a problem, using orbitals, but an orbital per se is a one electron wave function. That's what it is. Nothing more, nothing less. I hope, Ishita, you are answered. And Prashant has said, repeat once again the second equation. The second equation, if I understand you correctly, is this, or maybe I'll just say it once again. First of all, in order to construct the MOs, I take a linear combination of the pendant atom orbitals, the 1s orbitals. So we take a linear combination of this 1s wave functions, and now let us call that wave linear combination psi hs. I'm constructing the MO by taking a linear combination of the 2s wave function of carbon atom and psi hs. So psi hs is written in an expanded form here. There are two coefficients, C1 and C2. I don't know yet what they are. We can figure out later on, not today. And there is no justification for me to use only plus sign. I can use plus, I can use minus. If I use plus sign, then if 2s has plus sign, then P, Q, R, S, all these 1s wave functions have plus sign. That is the bonding molecular orbital. If I use minus sign, then when 2s orbital has plus sign, then PQRS will all have minus sign, and that will be the anti-bonding orbital. Next question is, why common coefficient is taken for all the hydrogen atoms? Because they are all identical. There is no reason why the hydrogen atom 1s wave functions should have different contributions from, one from the other. Okay, Ishita's doubt is cleared. Great. Happy to hear that. And so that is why they are all same. So there's no reason for me to take one small p and one large q. There will be situations later on when, even though they are same, you have to take different weightage, but not for this case. Okay, on what basis you put PQRS on those particular corners of the cube? So the way you draw a tetrahedron, unfortunately, I'm not being able to annotate here. The way you draw a tetrahedron always is put a dot anywhere. Instead of this, I could have chosen this vertex, doesn't matter. What I have to do is, if I put the dot here, then I have to leave aside this next vertex and the next vertex, and then put the next dot here. Similarly, from here, the immediately next vertex cannot be populated. You have to go to the other one. That is a standard way of drawing a tetrahedron in a cube. Yashaswini is absolutely right. Okay, moving on. This is the symmetry adapted linear combination of 1s orbitals. Remember, what we are doing is we are taking a
Is there some problem?
I'm back. I'm back.
Okay.
All right. So this is hopefully everybody had. This is what everybody has seen, I hope. So we have linear combination of the pendant atom wave functions with symmetry that is compatible with 2s orbital of carbon atom. Okay. Now, there's a question from Sudipa. Here, which contribution is more, carbon or hydrogen? I want to know which coefficient is of greater value, C1 or C2. To do that, what you need to do is you need to write a you need to go a little further. You have to write down Schrodinger equation with this Hamiltonian and the wave function, and okay. Well, so yeah, you have to actually write. So you end up getting a system of linear equations, and then with a little bit of manipulation, you get something called a secular determinant that is equated to 0. That's how you find the coefficients. So we are not discussing that today, but if you want to know further, you can this from Macquarie's quantum chemistry book. Right. There was some other question. Let me answer that first. Am I audible?
Yes, sir.
Okay. Yeah. So to answer Shreyas, an orbital is one electron wave function. What if there is one more electron in the same orbital? Then we start with one electron wave function, and we pretend as if we can put. That's a very good question actually, because I'll actually elaborate the question a little more for you, Shreyas, even though we are digressing from our agenda, but that's fine. What you're saying essentially is, even for many electron atoms, we talk about electron configuration, and you talk about 1s2, 2s2, and so on and so forth. How do we do it? My slides are not visible. I'll make them visible. Yeah. Sorry for multiple interruptions. Okay, I got logged out again, but now I'm back once again. Let us hope this will not happen again. So, what was I saying? I was trying to answer Shreyas's question. So, what you need to do is you need to actually modify the wave function. The first way you can modify is bringing in effective nuclei and try to live with it. But sometimes it doesn't work, and you have to change the wave function completely. So that takes us into a little more detailed discussion of quantum.
Sir, are you there? I think there's some network issues, so kindly bear with us. Sir will be back. So were you able to connect? So can you hear me? Sir is having some network issues. He's going to rejoin again, so kindly bear with us. There is some technical problem with Professor Ananya Datta's computer, and he said that he will restart in 10 minutes after rectifying it. So kindly bear with us. You may try to just go through whatever he has discussed and try to see if you have understood and come out with some questions. So he'll be joining us as soon as his computer is rectified. So he's asked me to make the announcement that he will be coming soon. So please wait.
Hello, sir.
Right. Am I audible? Can you hear me?
Yes, sir. We can hear you.
From two computers. Let us see if that helps at all. I'll also log into this YouTube from a different place. Hold on a sec, please. YouTube from a different place. Hold on a second. Okay, maybe that's why I was hearing something. All right, we are ready.
Hello, sir.
Yes, ma'am. Yes, ma'am. I'm there. Right. Am I audible? Can you hear me?
Yes, sir. We can hear you.
There is a problem with the network. That's the issue. But anyway, let's try. Yes, I'm there. Please wait a minute. Okay, maybe that's why I was hearing something. All right, we are ready. Can you see my slide now?
Yes, sir.
Okay. So let's hope there's no further hiccup. Problem is network quality is very, very poor today somehow. So we'll begin.
Yes, sir.
Okay.
Your slide shows insurance meeting, etc., etc.
Huh? No, no, no. That's what you're saying?
Yeah, that's what I'm seeing on the Teams.
Let me try to get it once again.
So you have shared the wrong screen.
I think so. I stop sharing.
Yes, sir.
And okay, got it.
Yeah, now it is seen.
Yes. Problem is I'm getting constant messages saying network quality is bad. So if I get cut off this time, I'll try to join with this. Oh my God. Now everybody knows what meeting we had. Anyway, so if I get disconnected, I'll try logging in with my mobile phone network. So let's try and begin once again. Extremely sorry for all this goof up, but this is really something that is not in our hand. Now the problem is I'm not able to see the chat window. Yeah. So we are discussing methane. We are trying to develop what is called a delocalized molecular orbital theory picture for methane. And what we try to remember while doing this is that atomic orbitals with proper symmetry can only be combined. So we said that you have two kinds of valence shell orbitals in carbon atom, which is at the center, 2s orbital and 2p orbital. And obviously, they have different symmetries. So if you apply, let us say, right? Maybe you will not be able to see it very well, but if you apply a C2 operation, remember where the C2 axes were in our discussion yesterday along X, Y, and Z? And if I apply C2 axis and if I hold the C2 axis like this, now I can annotate. That's great. Let us say this is my C2 axis. Remember, joining the opposite phase centers. If I turn with respect to the C2 axis, then what will happen? The wave function will remain the same. Now think of this. I apply this C2 axis to the 2p orbital, turn by 180 degrees. The wave function remains the same, no problem. But remember, there is another C2 axis from here to here and from here to here. Well, they should overlap. They did not overlap because of my poor artistic skills. If I apply one of those C2 axes, let's say I apply this C2 axis and turn by 180 degrees, what will happen? The top lobe will come to the bottom. The bottom lobe will go to the top. And so, instead of Px, Pz or whatever it will be called minus Pz. So what I'm trying to say is that with respect to some of the symmetry operations of a methane of tetrahedral point group, the 2p orbital can change sign, whereas the 2s orbital does not change sign in response to any of these axes. So the symmetry of 2s and 2p orbitals are not the same. Well, I will not be visible. I cannot help it really. Right now, it will not be possible for you to see me, but we'll do that later. Okay. So let us focus on the presentation, and if you can hear me, then it's fine. Okay. So now, what we are saying is, what we had said all this already is this, that in order to construct the molecular orbital, first thing we do is that we take a linear combination of hydrogen 1s orbitals which have matching symmetry with, say, the 2s orbital. That means with respect to all those C2 axes, they should not change their sign. So the combination of 1s orbitals that satisfy this criterion is P plus Q plus R plus S. When I say PQRS, I mean the 1s orbitals of PQ, R, and S. And we take a linear combination. This is called a symmetry adapted linear combination. In order to construct the molecular orbital, we take an appropriate linear combination of the central 2s orbital of carbon atom and the linear combination P plus Q plus R plus S. We can combine using plus sign or minus sign. If you use plus sign, then it is the bonding orbital. If you use minus sign, then it is the anti-bonding orbital. That's what it is. Now, there were some questions about this that were asked. You asked, what is C1, what is C2? The answer to that question comes from a little more of quantum mechanics. You can use variation theorem or whatever you want to use, and you can actually set up equations which are called secular equations by which you can find out the coefficients. We are not going to discuss that today, but what we will discuss is how the symmetries are different. Okay, that's what we are focused on in today's discussion. Now let us come to the 2p orbital. In 2p orbital, what happens is we already said that the symmetry is different. If you apply some of the C2 axes, this is changing. If you apply some of the planes, then also the symmetry can change. So let us write the sign of the orbital, then perhaps it's a little easier to understand. Let us say this slope has plus sign of wave function, this slope has minus sign of wave function. Now, what is the symmetry of PQRS that is required in order to get bonding and anti-bonding combinations with your central 2p orbital of carbon atom, of the 2p orbital of the central carbon atom. I'm sorry, I am a little flustered because of all this trouble, but just bear with me for a few minutes. Okay, so now see, on top, let me just draw this plane. Okay. Think of this plane. On top of this plane, the p orbital has plus sign, and at bottom of the plane, the p orbital has minus sign, right? Now see, in order to have right symmetry, this s orbital of p should have plus sign, s orbital of q should have plus sign, s orbital of r should have minus sign, and s also, the one s orbital of capital S also has to have minus sign. Okay. So what is the linear combination we need? P plus Q minus R minus S. Okay. This linear combination has compatible symmetry with the p orbital. Remember, this is called a symmetry adapted linear combination. Well, Saurabh, that bar is something that I also see in this, but it is not there on my computer. I do not have control on it. Sorry. And to answer the question of Gyan Pratik, you said for S orbital, the wave function cannot change sign. Does that mean initially it can be either positive or negative sign, or is it only positive? It can be anything. Positive, negative, these are all relative. It depends on us what we define as positive, what we define as negative. It is not really written on the wave function just like that. We write it. Okay, so it could be anything. Okay, so I hope this part is clear. If there's a question, I stop for a little while. Please ask. Do you understand that psi 1s, or maybe I'll write it here? Well, you can ask the question anyway. Okay. So what I'm saying is, psi 1s of P, forgive the bad handwriting, it is not easy to write using a trackpad. In any case, even if I write using the best fountain pen, my handwriting is bad. If I take this linear combination, P plus Q, I'm taking all 1s orbitals, plus R plus S. This has plus sign everywhere. So that would not be compatible with this p orbital. Okay. But if you take p plus q minus r minus s, then you have compatibility with the p orbital. That is what we call matching symmetry. Now, with this symmetry adapted linear combination, I can take appropriate linear combinations of this 2p orbital of carbon to generate bonding and anti-bonding molecular orbitals. If you have question, please ask now. If you have question on this part. Maybe I'll go ahead and as questions come, I'll answer. This lag is too much. Now see, there are three such linear combinations, isn't it? You might remember that I had said that this is z-axis, this here is x-axis, this is y-axis. So I can take px, py, pz, and accordingly, I can take appropriate linear combinations. If this is pz, then the appropriate linear combination is p plus q minus r minus s. If I say, let me first erase this. I've drawn too many lines. Let me erase and then we'll start again. Suppose I draw my orbital this way, and I call this px. Let us say this is plus and this is minus. Now see, if you take p plus q minus r minus s as before, then what will happen? Am I still there, madam?
Hello.
Yes, you can hear me, right?
Yes, sir. Yes, sir.
Okay. Okay. Because out of two computers, one got disconnected, but that's fine. Okay, I'll go ahead then. So I can have three such linear combinations, x, y, and z. But before that, Shugato has asked a question. Are we assigning signs on R and S opposite to P and Q just because they are in a diagonally opposite position? No. We are assigning negative signs to R and S so that they have the same sign as the lobe of the p orbital that is closest to them. Because then only we can have bonding and anti-bonding combinations. Okay, we can take either plus or minus. If we let us see if you understand better when I take the next example. How only one lobe will combine with two atoms? No, no, no. I mean, see. Okay, Sushant, we are working on delocalized molecular orbital theory here. So to construct the molecular orbital, it is not required that I'll take one atomic orbital from carbon, one atomic orbital from hydrogen. I can take as many number as I require. In the ideal case scenario, I should take 2s and 2p of carbon atom, and I should take the four 1s orbitals of hydrogen atom. I'm not doing that, and I'm reducing the problem a little bit by taking combinations of only the central atom orbital and symmetry adapted linear combinations of the pendant atoms that have compatible symmetry. Why are we talking about only C2 symmetry elements? It's only an example. But this infinite symmetry is not the issue. So Pranav, it's important to understand here that we are talking about symmetry of the molecule. The molecule is not d infinity h or anything. The molecule is tetrahedron. There we do not have, if you take the 1s orbital in isolation, then you can say it's a perfect sphere and it has infinite number of symmetry elements of all kinds. I'm not taking it in isolation. I'm taking it as a part of the molecule. So we are working with the symmetry operations that are present in the molecule itself. Right? Let's get ahead. Now see, the linear combination we had constructed first, p plus q minus r minus s. Does it have the same symmetry? Does it have compatible symmetry with px? For px, this is a plus slope, that is a minus slope. So this plus slope gets to interact with a plus slope from q minus slope of s. That is non-bonding interaction. The minus slope of p gets to interact with a plus slope of hydrogen atom p and minus slope of hydrogen atom r. So non-bonding once again. So what I want is, if I want to construct a linear combination with px, this is px, then the appropriate linear combination is, and I'm only writing capital P, capital Q now, right? I'm not writing 1s and all. So the appropriate linear combination is Q should be positive, okay? S should be positive, P should be negative, and R should be negative. And if I want to write in alphabetical order, I should write minus P plus Q minus R plus S. This is the appropriate symmetry adapted linear combination for this Px. Please tell me if you have understood this. So for Pz, I need P plus Q minus R minus S. For Px, I need minus P plus Q minus R plus S. Can somebody tell me what kind of symmetry adapted linear combination I'll need? And let me clear up the screen a little bit for you. What kind of linear combination will I need if I want to work with the py orbital? I'll draw the py orbital for you, the way I'm defining p, the way I'm defining y. Py, the plus slope is pointing towards us. The minus slope is away from us. Can you tell me what will be an appropriate symmetry adapted linear combination of P, Q, R, and S that can give me bonding and anti-bonding interactions with P, Y? While I wait for the answers to my question, I'll just answer one or two questions on the chat. R plus Q minus P minus S. Excellent, Ahi. So that is the right answer. If you want a linear combination with Py, you have to take R plus Q minus P minus S. And so what we see is that there are three such linear combinations: one for P, one for Px, one for Py, one for Pz. So Ishita, you're right. R plus Q minus P minus S. Pranav, you're right as well. Excellent. We'll go ahead. So what we see then is that when we construct these molecular orbitals, there are two kinds of molecular orbitals. One is like this, right? Yes, everybody has got it right. Tejasri, Pranav, Vasudevan, Kavita, Shampurna, Siddhi, Saurav, Nitro, everybody has got it right. Excellent. So see, we have understood it nicely. So we have two kinds of molecular orbitals, one with 2s, one molecular orbital, no node, and we have three molecular orbitals of a kind in which the participating atomic orbital of carbon is 2p and not 2s. There is a node. Now I lost the YouTube connection. Okay, I'm back. So all of these functions are dependent on x, y, z variable. Actually, yes, they are. You write these in terms of x, y, z, or better still, r theta phi. Okay, so let's come back here. So we have two kinds of molecular orbitals. So just from symmetry, what we are saying is that we should have two different kinds of MOs. All MOs are not the same. And the rule of thumb that we usually use is that greater the number of nodes, higher is the energy. So we can construct an energy level diagram like this. And I'll show you some experimental evidence in favor of this model. So this is 2s and 2p for carbon. And here we have the four 1s orbitals. What we need to do is we need to take first a combination of 2s and the appropriate linear combination. Remember, p plus q plus r plus s. With that, we'll get a bonding orbital when we take the combination of plus, and we get an antibonding orbital when we take the combination of minus between 2s and the linear combination. So maybe what I'll do is I just write this one is 2s of carbon plus P plus Q plus R plus S, 1s orbitals. What I have not written here are the coefficients C1 and C2, but they're very much there. And this one is 2s of carbon minus P plus, I'll just write dot 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 Q plus R plus S. Okay, so we have got a bonding and an antibonding orbital using the 2s orbitals, 2s atomic orbital of carbon. Now, what is left? I'm still left with this 2p orbitals, three of them, and I can make, excuse me, I can prepare the appropriately symmetry adapted linear combinations with the carbon orbitals, with hydrogen 1s orbitals. Using them, I get 3 bonding MOs that are degenerate and 3 antibonding MOs that are degenerate. All right. So this is the picture that we get for methane, qualitative picture, just using the insights generated from symmetry. If we did not use symmetry, we might as well have thought that all the 4 molecular orbitals have the same energy. Okay, let's go ahead and we'll come back to this. Is 2s of carbon energy less than 1s of hydrogen? Actually, it is. I draw it that way because we know it from experiment and also from theory. So now let me fill in the electrons. How many electrons will be there? 4 pairs, right? So this is 1, 2, 3, 4. Now see, I will be disappointed if none of you is disturbed by what I have drawn. We know very well that in methane, all the 4 bonds are equivalent. That's why it's a tetrahedron in the first place. All are carbon-hydrogen bonds. Here I am telling you that the 4 MOs are not equivalent. I have one MO of one kind, which uses the 2s orbital, and I have 3 MOs of another kind, and these MOs use 2p orbital. So that is something that is new, that has come up because we considered symmetry. Now the question is, aren't 2s and 2p orbitals of carbon hybridized and have some energy? Hybridization is something that we do. Hybridization is a valence bond theory concept, and it is used to generate your directional orbitals. The moment you resort to hybridization, you give up on the biggest advantage of molecular orbital theory, that is delocalization. That is why we are not using hybridized orbital. Please remember, hybridization is sort of our way of understanding directional bonds. Hybridization is not the cause. Yeah, my question 2 that then I have answered is 4 times 1s written above 2s because of them being 4. Yes, there are 4 1s orbitals, right? There are 4 hydrogen atoms. So each hydrogen atom contributes 1 1s orbital. Why energy of 1s of H is greater than 2s of C? That is because your nuclear charge is more in carbon, and then you have to consider shielding, screening, all of these things. And that is why, as you go higher up, the energy of orbitals actually keep going down. Fine. Now see, but let us come back to what we are saying. We are saying that there are 2 kinds of molecular orbitals, and we are saying this from consideration of symmetry. Well, before showing that, Max Planck had said that experimental results are the only truth. Everything else is poetry and imagination. Not to undermine poetry and imagination, they are what set human beings apart from other animals. But then, science is the pursuit of truth, and so we'd better show you some experimental result before we can claim that what this beautiful poetry and imagination that has come out of consideration of symmetry is correct. That experimental evidence is available in the form of photoelectron spectrum. Now, without going into the detail of photoelectron spectrum, let me just tell you that this is a measure of ionization energy. This is a way in which you measure ionization energy. And all those questions you're asking, that how do you know that 2s orbital has lower energy than 1s orbital of hydrogen? I know it from photoelectron spectrum. Okay? So what it means is this. You see in the photoelectron spectrum one band at ionization energy of around 2100 kilojoule per mole. And that's a small band. You see another big band at around, say, 1300 kilojoules per mole. So what it says is that there are 2 kinds of ionization energies. And it also says that the population of the state or orbital with lower ionization energy is 3 times the population of that of the lower ionization energy. Where did this 3 times come from? Well, 3 times came from the fact that the area here, now what happened? The area under this curve of lower ionization energy is 3 times the area of this smaller band. So now see, what is the meaning of ionization energy? You have to promote an electron from wherever it is, in whichever molecular orbital or atomic orbital it is, to infinity, right? So this is the ionization energy of what we have drawn, the triply degenerate MO. And this is the ionization energy of the single MO that has formed due to participation of 2s orbitals. Now, which one is more? Obviously, this one is more. This is what we assign to the smaller band at higher energy, and this is what we assign to the band with a larger area at lower energy. So experimentally, we get to understand actually there are 2 kinds of MOs. two kinds of energy levels. Of course, bond lengths are equal. That is not wrong. Yes, you can get the presentation, but let our session get over, please. I'll share it. No issue. Bond lengths are equal. So, is that a conflict? We are saying we have two kinds of MOs, but then we are saying there's only one kind of bond. Is there a problem here? Actually, there isn't. It is important to understand that bonds and MOs are not one and the same. When you talk about molecular orbitals, you want to know about these energy levels. When you talk about bonds, you talk about electron distribution between two atoms. Okay, so they are not one and the same. To get bond length, you can do different kinds of experiments, X-ray crystallography or microwave spectroscopy. And in quantum mechanics, there is something that is very beautiful, which says that properties of the observable depend on the observer. Depending on which experiment you perform, you get to see the properties. You have learned in the quantum session that you use an appropriate operator on the wave function to learn about the corresponding energy. Here also, the experimented analog of using an operator is to do a spectroscopy or crystallography or microscopy or something like that. Depending on which experiment you do, you get to know about some property of the molecule. Okay, so this VB and MO pictures are actually correlated, and all MOs contribute equally to each bond. So that is the resolution. Bond, remember, is the electron density between two atoms. Molecular orbitals are wave functions. They are delocalized all over the atom, all over the molecule. So when you consider any two atoms, well, carbon atom and any of the hydrogen atoms, that space has equal contribution from the electrons in all the MOs. So the end result is that all bonds are equivalent. Okay, so the reason why we wanted to discuss this is to demonstrate how quantum mechanical problems can be simplified and how you can get insight into quantum mechanical problems even before doing actual quantum mechanics using symmetry. Okay, so that is the first part of today's discussion. Now, please ask questions on this part, and then we'll try to, or maybe I'll go ahead and say a little more, and then we'll take questions. You can start typing the questions already, but let me go ahead a little bit, and then we'll talk about the matrices. Now, see, we are talking about symmetry types. What is the meaning of symmetry types? Some of you asked, why is it that we are only talking about C2? We are not talking only about C2. Actually, for a tetrahedron, you might remember that the symmetry operations that are there are E, identity, C3, there are 8 C3s if you remember from yesterday, 3 C2s, 6 S4, 6 sigma Ds. What we want to see is what happens when each of these is applied. Now, think of that 2s orbital. No matter which symmetry operation you applied, they would not change, right? That is what gives these values of 1. So what I'm saying is you take any symmetry operation and write an operator for it. Let us say I call it R. That R operates on the wave function phi to give me some eigenvalue R multiplied by the same wave function phi. By now you are familiar with eigenvalue equations. So this eigenvalue that we get, small r, is listed here. And you can think that that is the response of the wave function to the symmetry operation that we apply. Now, when we want to talk about symmetry type, it is not enough to discuss only one symmetry operation. So you understand that if r is equal to 1, then phi remains unchanged. If r equal to the small r equal to -1, then phi changes sign. If r is equal to something else, then there would be distortion. We'll get to that. So if r is equal to 1, then we say that the wave function is symmetric with respect to that particular symmetry operation. If it is -1, then we say that it is antisymmetric with respect to that symmetry operation. Antisymmetric. So what we see is that suppose something is symmetric with respect to all the symmetry operations, then we call it the A1 symmetry type. A1 means totally symmetric. Well, this is Mulliken nomenclature. I don't think we have time to go into this in very great detail. Just accept that a totally symmetric function has A1 symmetry. Okay. Now, so what about that linear combination? P plus Q plus R, that's R not K, plus S. What happens when I apply, say, C3 on it? C3 operating on P plus Q plus R plus S. What will I get? Let me just go back and show you what PQRS are. You need the names, right? Yeah. So see, I apply a C3, and I might as well erase this thing. Where is C3? Remember, C3 is along a bond. So let us say this is a C3. If I apply this C3, what happens? P remains P, Q becomes S, S becomes R, R becomes Q, isn't it? So P plus Q plus R plus S becomes P plus R plus Q plus S, or in other words, it remains the same. So similarly, you can do this exercise with all the other symmetry operations, and you'll see that this P plus Q plus R plus S does not change in response to any of the symmetry operations. Okay, so this P plus Q plus R plus S also belongs to this A1, what is called symmetry species. What you see here is a character table. A character table is a compendium of the symmetry species. Symmetry species means each of these lines is a symmetry species. So A1, what we are saying is symmetric with respect to E, symmetric with respect to C3, symmetric with respect to C2 and S4 and sigma D. A2 would be symmetric with respect to E, symmetric with respect to C3 and with C2, but antisymmetric with respect to S4, antisymmetric with respect to sigma D, and so on and so forth. Okay. Now, so this way we try and match the symmetry species. What about your XYZ, and what about the P plus Q minus R minus S kind of wave functions? Well, they belong to T2 species. Okay. T2 is a three-dimensional representation. Okay, these are also called representations. What it means is that when you apply this C3, you end up mixing all these wave functions, and that is why you cannot handle them by themselves. That's a little more complicated. We do not have time to get into that today. Until now, the take-home message is that symmetries have to be compatible between the central atom wave function and the symmetry-adapted linear combination of wave functions of the pendant atoms in order to form the MOs, may it be bonding or anti-bonding. Okay, and what we have said in a very, very sketchy manner is that all the symmetry types of symmetry species are nicely compiled in what is called character table, and how the response comes for each of the symmetry operations is given by these numbers, which are called characters. How do we generate character tables? That is what we want to discuss once again a little sketchily in the next part, and that takes us to matrix representations of symmetry operations. Before going there, if there is any more question, can you please ask? I'll stop a little now so that you can type in your questions, and as usual there is a lag, can't do much about that, but thankfully the first question has come. How can anything be distorted by an identity transformation? It perhaps Pranav's question comes from the fact that I've written 3 here. Pranav, is that right? Problem is, by the time you'll give the answer, I'll move on because there's this time lag. So it does not get distorted by identity operation. Something else happens. Maybe hold on to the question. Let us discuss a little bit about your matrix representations. Hopefully your question will be answered. If it's not answered, please ask at that time. Next question from Chris is, what is A1? A1 means, suppose you have some function that is symmetric with respect to each and every symmetry operation present in that point group. That is why we studied point groups yesterday. Any function that is symmetric with respect to each and every symmetry operation in the point group is said to have A1 symmetry. For now, please go with this definition. Okay, next question from Pranav. Why are there eigenvalues not equal to 1 for each symmetry operation? I believe that is the same question that, oh, okay, you asked the question. Yes. So it is, let's come to the matrices. I'll give you an answer to that. Okay. Any other question? Anyone? Well, we'll move on since no question has come for the last couple of minutes or so. Now, in order to get this character table, we need to take a step back and we have to learn how one can represent symmetry operations by what are called transformation matrices. Okay, first we'll come to identity. Let us say I'm working with XYZ coordinates of a particular point, or maybe unit vectors along XYZ direction, or, well, whatever. So XYZ, when we want to perform identity operation on XYZ, I get back XYZ. So if I write XYZ as a column matrix and I write and I get another column matrix as the answer, I have to left multiply this column matrix by a unit matrix that will be 3 by 3. That is the transformation matrix for identity. Okay, very easy. So while you digest that, I'll answer the couple of questions that have come. Good evening, sir. Yes, good evening, Srinivasalu. Shushrut Shubham has asked, how to transition shown in previous slide, but there are 2 vacant and 2 filled orbital? No, the transitions, we are talking about photoelectron spectroscopy there. In photoelectron spectroscopy, you promote to infinity. So you give so much of energy to the molecule that it gets ionized. And you try to measure the kinetic energy and try to figure out what the ionization energy is. Okay, so this is not a transition from one energy level to another energy level of the molecule. It is transition from one energy level all the way to infinity. That means the electron is lost. The molecule has become ionized. That's why it is called photoionization spectroscopy. If you want to know more about it, we'll take it at the end of our discussion. All right. So I hope everybody have understood identity matrix. Now we'll go ahead a little bit. Let us talk about reflection. I'm not even saying which point group it is or any such thing. Let us talk about reflection with respect to X, Y, Y, Z and ZX planes. Okay. And now I'll do this myself. Next one, I think you can handle it. You'll be able to give me the answer. See, X, Y, Z, let me draw the axis. Conventionally, we write this as Z. This is X. Then pointing towards us, we'll get Y. Now see, let us consider reflection with respect to the XY plane. XY plane means this plane. What will happen to X? X and Y are on XY plane. That is sort of stating the obvious. It's called XY plane because X and Y axis are on the plane. So what happens when you take a reflection of X or Y for that matter in the XY plane? X remains X and Y remains Y even after reflection. What about your Z? Z is above the plane, right? Plus Z is above the plane, minus Z is above the plane. So when I do reflection with respect to this XY plane, will you agree with me that Z becomes minus Z? Yeah? So reflection on XY plane keeps X intact, keeps Y intact, transforms Z to minus Z. Okay, so I know where I started from and I know the answer. Now I have to figure out this 3 by 3 matrix. Can you tell me now, and now I'll wait for your answer. Can you tell me what the first row is going to be of these of this 3 by 3 matrix? Please write what I'll have in the first row of this 3 by 3 matrix if I have to transform XYZ to XY minus Z. Remember, matrix multiplication is row multiplying columns. Z2 minus Z. That's right, Ahi. You answer my question. Feel feedback form later. One zero zero, excellent, fantastic. So 100. Now, what about the second row? Please write second row and third row to save time. Yes, everybody's got it right. Very good. 010 second row. Very good, excellent. And third row? What about third row? 00 minus 1. Excellent. So somebody said 1 1 minus 1. That was also a correct answer because what he did is he wrote the diagonal elements only. Okay, so this is what we have got. And do you agree with me that these numbers that we are getting are really the eigenvalues, right? Eigenvalue of reflection. Fine, we go ahead. Now this is a little more interesting, rotation. But what I'll do is, since we want to get somewhere, I'll just skip this because this is geometry. Okay, you can do it yourself, and it is discussed in the Symmetry and Spectroscopy book by Harris and Bertolucci. So when you rotate by theta, then using all these geometric relations that we've all studied in school, very simple. And I'm going to share the slides. I just send them to madam, and madam can share in the best possible way. This is what you get: cos theta, sin theta 0, minus sin theta, cos theta 0, 0, 0, 1. Okay, so this is the matrix for rotation, and you can block factorize. Means you can break it down into two blocks. You draw this vertical and horizontal line, you get this cos theta, sin theta, minus sin theta, cos theta, and you get 1. Okay, very good. Everybody has got that question right. Now see, if you turn clockwise, then you get this matrix: cos theta sin theta 0, minus sin theta cos theta 0, 0, 0, 1. If you turn anti-clockwise, then you get cos theta minus sin theta 0, sin theta cos theta 0, 0, 0, 1. So if you look at the character, what is the meaning of character? This 1, 1 element plus 2, 2 element plus 3, 3 element. Okay, diagonal element. So you just sum along the diagonals. What do you get? You get 2 cos theta plus 1. Here also, you take this diagonal element, you get 2 cos theta plus 1. All right. So remember, Cn plus and Cn minus also belong to the same class, rotating clockwise or rotating anti-clockwise. So same symmetry operations of same class have the same character. Now, if you go back and think of the character table, I told them their eigenvalues. That answer was only partially true. They are eigenvalues for what we call one-dimensional representation. For more than one-dimensional representation, they are they are actually the character. Okay, that is how you can get 3 as identity for as 3 as character of identity matrix. Okay, let us see if we have a chance to elaborate upon that later on. Okay, now what I discussed so far, that these are the transformation matrices. To generate what are called representations, we have to consider all transformation matrices. So I like to equate this to marks obtained by a student. You want to know about the performance of the student in a particular year. It is not enough if I say the student has scored 100 out of 100 in physical chemistry, isn't it? The student might as well have scored 5 out of 100 in organic chemistry. I mean, if I'm the student, that's what is going to happen anyway. So what I need to say is, what are the marks in physical chemistry, organic chemistry, inorganic chemistry? Then only will I be able to say what is the performance of the student in chemistry. Okay. Similarly, in order to understand the symmetry behavior of anything, we have to talk about all the transformation matrices together. That collection is like your report card. It is called the matrix representation. Shugato has asked, agreed that these corresponding eigenvalue, not asked, answered. Very good. And Pranav is saying character is trace of the linear transformation, not the eigenvalue. Yes, it is just that when you have 1 by 1 matrix, it is just a number. Then it is the eigenvalue in itself. Okay, let's see if we can get to that. Great. So now for C2V, for example, let me see what happens if I take XYZ as the basis. What are the transformation matrices I get? I can write down E for you. E, of course, is 1, 0, 0, 0, 1, 0, 0, 0, 1. What I would like you to do is, can you work out, well, there will be a time lag again. So what I'll do is I'll work out the matrix for C2, and I'm taking C2 to be the z-axis. Can you work out the elements for while I work out C2 and sigma B? Okay, C2. What happens when I apply C2 along z-axis? I'm getting bad network quality again. I hope I'll not get locked out. So what I'm saying is C2V, let us say this is the z-axis, and I'm using the z-axis as the C2 axis. Where is x? Let's say this is x. And then actually I had drawn that thing a little in the opposite way last time. So why should be here, isn't it? If it's a right-handed system. So this is x, this is y, this is z, and don't forget that this is minus y, minus x, and minus z also. So what happens when I turn by 180 degrees? What happens to x? Do you agree with me that when I turn by 180 degrees, x becomes minus x and minus x becomes x? Yeah, so x becomes minus x. So what will the first line be? Minus 1, 0, 0. Similarly, y becomes minus y. So 0, minus 1, 0. What about z? Now you're turning with respect, you're turning about z, isn't it? So z does not change. So you get 0, 0, 1. Madam, can you just provide them the feedback link? I'm getting distracted if so many people ask for feedback link in the chat window. I'm looking at the chat window for questions. So,
Sir, actually, we have already informed them about the feedback thing.
We have
Can you
already
set-
told them, sir, that it will be put up only at 4:30. So, I mean, I think they should understand that we'll be doing the needful at the correct, appropriate time.
yeah. So my request is please stop asking for feedback link. Only discuss things that we are discussing scientifically. Otherwise, it is very distracting for me. Thank you. Okay. Sigma v zx. Well, Ahi has already given zx. Let us see, Ahi, if you have got it right. 1, 0, 0, 0, minus 1, 0, 0, 0, 1. Excellent. So it's the same thing, right? Z and x will not change sign. Y will change sign. Sigma v dash. Sigma v dash is minus 1, 0, 0, 0, 1, 0, 0, 0, 1. So we have been able to construct the transformation matrices. And yeah, diagonal is 1, minus 1, 1. But hold on a minute. We are going to do something more. We'll not just add up the diagonal elements and write one character for this. In fact, we'll see how this entire thing collapses into not 1, but 3. Oh, man. We'll see how this collapses into not 1, but 3 representations. See, neither of the symmetry operations that we have used mixes wave functions. Well, in this case, mixes functions, x, y, z, right? So x either remains itself or becomes minus 1. So it has to be either symmetric or antisymmetric with respect to C2. Sigma v, well, y has to be either symmetric or antisymmetric with respect to any of the symmetry operations that we have chosen. So we don't even have to consider the off-diagonal links, off-diagonal elements. We can only consider the diagonal elements here. So what we do is, we don't care about anything that is beyond these vertical lines that we have drawn. Okay, these zeros mean no contribution. So what we do is, we get rid of the zeros, write them nicely, and now what have we got? We have got the information that x is symmetric with respect to E, antisymmetric with respect to C2, symmetric with respect to Z, sigma v zx, antisymmetric with respect to sigma v dash yz. Y is symmetric with respect to E, antisymmetric with respect to C2, antisymmetric with respect to sigma v zx, symmetric with respect to sigma v dash yz. Z is symmetric with respect to everything. So we have got not 1, but 3 representations, 3 symmetry species. So now what I'm saying is that each of these representations is a symmetry species, And symmetry species means what is the behavior of a function in response to each and every of these symmetry operations. It's like the report card that gives you marks of organic as well as inorganic as well as physical chemistry. Okay, so you get a more holistic picture. All right, and each of the symmetry species have some name. Okay, the last one, 1111, that is totally symmetric. Totally symmetric means symmetric with respect to all the symmetry operations that are there. So that is A1. The others are B1 and B2. But let us see if we can get it to them. Now I want to introduce one more term, and that is irreducible representation. See, here we have 1 by 1 matrix, which means a number. It doesn't get any smaller. Can you get half a number? You cannot, right? I mean, half is a number, but you cannot get half a number. You can only get 1 by 1 matrix. It doesn't get any smaller. So that is why you cannot reduce these representations any further. So these are called irreducible representations. So all one-dimensional representations, one-dimensional means where we can break down nicely into numbers like this. These are irreducible representations. But you can have two-dimensional representations that are irreducible as well. Okay. Now, I'll just show you the result of these matrices that we can get using a different basis. Now, we are going to, okay, why block distribution is done? One scientific question at last. Why block distribution is done? Because if you look at this, there is no off-diagonal element here, right? An off-diagonal element would mean, suppose I had a 2 here, what would that mean? That would mean that there's a mixing of x and y. You perform E on x and you get 1 multiplied by x plus something else multiplied by y. You are getting actually 1 multiplied by x plus 0 multiplied by y plus 0 multiplied by z. So since all off-diagonal elements are 0, we can do block factorization. Okay, now, if you use the atoms as basis, I request you to work this out yourself. I'll just show you the answer for the want of time. These are the matrices you get. And once again, you can do block factorization. But now see, I cannot draw another vertical straight line which will leave an off-diagonal element that is non-zero. Suppose I draw a straight line here. What happened to my pen? Oh, it was an eraser, sorry. So suppose I draw a vertical line here. Then what happens? Then I have a non-zero element in that is left outside this block. Okay, I'll respond about that YouTube thing. It is already uploaded. So that is why I cannot block diagonals like this. I better get back my eraser and I better erase this. So I can only block diagonalize in such a manner that I have a one-dimensional block for oxygen atom and I have a two-dimensional block for the hydrogen atoms A and B. Why? Because think what happens when you apply C2. The hydrogen atoms A and B interchange places, don't they? Right? So they are getting mixed. This is called mixing. So if you use this basis A and OAB, where A and B are hydrogen atoms, A and B, both are hydrogen atoms. I'm just calling them A and B. So here, using this, you get a two-dimensional representation as well. So the one-dimensional representation is definitely irreducible. The two-dimensional representation may be irreducible, may not be irreducible. So we don't know. We don't know yet. So at this point, there should be many questions in our mind. The first question should be, is this reducible? Second question we can ask is, how many reducible representations are there? To answer this, there's something called great orthogonality theorem, which essentially says all these matrix elements are mutually orthogonal and well normalized as well. Something called group theory is used, and you generate 5 very important rules. We're not going to discuss this. Using these rules, you can actually generate the character tables. I'm sorry, I'm not going to go through all this now because this is half an hour's job. But using these, you can actually generate the character table, and you see that for C to V, you only have one-dimensional representation. We call them A1, A2, B1, B2. This is following the system proposed by Mulliken. So see, for C2V, we are discussing C2V, isn't it? We can have one symmetry species that is totally symmetric. All the characters are one. You can have one in which it is symmetric with respect to E, of course, symmetric with respect to C2, antisymmetric with respect to sigma V, antisymmetric with respect to sigma V dash. Or you can have symmetric with respect to E and sigma V, antisymmetric with respect to the others, or symmetric with respect to E and sigma V dash, antisymmetric with respect to the other two. Okay? This software is used for rotation. I have not understand the question, Navya. If you could please elaborate, I can try to answer. So that's what it is. And in fact, if you go to C3V character table, you actually have this. Sorry. You actually have this two-dimensional representation. Now, let me try to answer the question that was asked by Pranav long ago. How is it that you have a 2 in E? Is this distortion? It is not distortion. What I'm saying is this. See, if you think of the matrices, if you use X and Y as basis, what will be the matrix for E? It will be 1, 0, 0, 1. This is for E. For C3, what will be the matrix? Well, to know that, we have to go back to this thing that we did not derive today. See, remember what happens when you turn by theta. The character is cos theta, right? You add the two cos thetas, that is what it is. So cos theta sin theta minus sin theta cos theta. That's what it is. Okay, I think we are back. Remember, we are turning by 120 degrees. So can you tell me what is cos 120 degrees? What is sin 120 degrees? And we'll write this matrix. Meanwhile, let me go ahead and write the sigma V matrix. Sigma V matrix is 1, 0, 0, minus 1. That is why you get a character of 1. 1 minus 1 is 0. Okay. Now, I'm waiting for you to tell me what this cos theta sin theta minus sin theta cos theta will be. Just tell me what cos 120 degrees is, and we are answered. Have you understood why this is 1, 0, 0, minus 1? This is Z. This is your C3 axis. This is X. This is Y. Convince yourselves that the plane is like this. No, sorry, what I was saying. The plane is such that Y becomes minus Y and Z becomes, well, X becomes minus X. I just write the value of cos theta because looks like there is too much of delay, and I'll stop as well so that people can fill the feedback links and go home in peace. This is root 3 by 2, but we don't even care. We only worry about the diagonal, isn't it? Yes. Yes, Ishita, it's minus half. So I've written that now. It's a valid observation. The numbers we are getting here are positive or negative integers or 0. All of them belongs to set of integers. Not necessarily really. You can actually even get imaginary numbers. Okay? But see, what's happening here essentially is that when you apply C3, you are mixing x and y. You're turning by 120 degrees, right? So now x doesn't remain just x. X is minus x, minus half x, plus root 3 by 2 y. That is the meaning of mixing. And it is not further reducible. That is why these are the matrices that you have to work with. And that is how you get a character of 2 for E. It is not distortion. It is just a sum of the coefficient of x in x, of original x in transformed x, and that of original y in transformed x. Okay, Pranav, I hope your question is now answered. And just to complete this story, x and y actually belong to this E symmetry type. That's what we were talking about. Okay. Example of some more character tables, but we'll not discuss too much since our time is up anyway. Homonuclear diatomic molecules is supposed to be an infinity, and heteronuclear diatomic molecules, C infinity V. These are interesting character tables because there are infinite number of elements here. And that is all I want to say today. But before stopping, let me share something. Many of you have asked for these YouTube link and all. Actually, they're already there. So what you have to do is search for, I think, Anindya Datta symmetry. Let's see if that takes it. Yes or no. Well, that takes it to the NPTEL course. Let's go to videos. See, it is right there. The first hit that you get is this course that I actually recorded long ago in 2014. But all the lectures are now available on YouTube. But this is not it. So basically, go to YouTube and search maybe. All right. So I have a full course on symmetry, which I had offered through NPTEL, and this course is all the lectures of this course are actually available on YouTube. So please, I think you can download the material, the slides as well, but please try and you'll get it. Okay, that is for symmetry. And for those who are interested in quantum chemistry, let me just advertise a little bit. From 20th July, which is next Monday, I'm going to teach this course on quantum chemistry of atoms and molecules on NPTEL. So what you need to do is search for quantum chemistry of atoms and molecules with my name and go to this FIAM or NPTEL portal. It is a full 12-week, 60-lecture course. Unfortunately, we have not discussed symmetry there, but it's, I'd say, MSc first-year level quantum chemistry. But even people who are in BSc or BTech or something, I think you can follow. So whoever is interested in learning quantum chemistry further, welcome to enroll for this course. We already have 1,011 students across the country. And those of you who want the material or my lectures in symmetry, please find them on YouTube. And they are there. If there's any difficulty, please call me. Please send me an email, and I'll be happy to help out in whichever way possible. Okay, that's all for today. Thank you very much for your patience, and sorry for all this trouble that we had with internet connection and all, that is something that we had no control upon. Oh, oh, very sorry about that. I assume that the screen is going to be shown, but I had mistaken. Just hold on a minute. Hold on a minute, please. I'm afraid I don't know how to share the screen that way. So just search for my name and quantum chemistry of atoms and molecules, and you'll find the NPTEL course. Search for my name and symmetry in chemistry. I think you're going to find the videos that are there on YouTube. So that's all. I will be happy to take questions if you have any, other than the feedback link.
Are there any questions, sir? Because I'm on the Teams, I'm not on the YouTube.
Not right now. Okay, I think we are pretty much done, madam.
Okay.
Thanks a lot.
Thank you very much, sir. Before I conclude, I would like to request Dr. Ashok Kavle to propose a formal vote of thanks. Kavle, sir?
Yes, ma'am. Can you hear me?
Yeah.
Yeah, okay. Good evening, all. I feel honored and privileged to get the opportunity to propose a vote of thanks on this special day. I, on behalf of Department of Chemistry, Vizi was a college, and the entire fraternity of management here together, extend a very heartfelt gratitude to all the speakers for gracing your significant lectures and sharing with us your knowledge and opinions in both the sessions. I must mention our deep sense of appreciation for Dr. Arindam Chaudhary for sharing with us principles of quantum chemistry and understanding simple quantum chemical systems. Indeed, it was a pleasant meal for the quantum learners as reflected from the different questions raised by the keen learners. Sir, I'm sure your simplified conceptual explanation of difficult concepts, including quantum mechanics, must have cleared all the doubts of learners. The 3D images shown in the talk were very catchy and self-explanatory. I also convey my regards and hearty thanks to Professor Anindra Datta for an outstanding and informative talk on basic concepts of symmetry with examples of organic molecules. Understanding of symmetry elements using geometry concepts and its application in quantum chemistry using illustrative examples and models has truly benefited the learner to a greater extent. I take this opportunity to extend our most sincere thanks to Dr. Ruchi Anand, Secretary of Royal Society of Chemistry, West India Section, for her coordination and support to organize this two-day webinar. I also would like to thank our management, Principal Dr. B.B. Sharma, and our dynamic Head of Department, Dr. Gigi Kusalkar, for their constant support, encouragement, and guidance in the organization of this webinar. I also thank our faculty, Dr. Lakshmi Ravi Shankar and Ms. Khalida Sheikh, for meticulous planning and execution to make this event successful. I must thank our faculty from IT department, Ms. Purnima Madam and Rakhi Madam, for providing all the technical support throughout this webinar. Last but not the least, this webinar wouldn't have been successful without the participants. Thank you so much, all the participants, for paying your valuable attention. Once again, I want to state that we are almost grateful to all the speakers and participants. It's been a great pleasure. Thank you very much.